Welcome to We Are Faceless content, where you fall asleep smarter, not just quieter. Tonight we begin a full, highly detailed journey through quantum physics, from foundational theories to modern interpretations. You'll fall asleep to real science, with enough detail to satisfy even a physics student. Close your eyes, take a breath, and let's explore the quantum universe together. Chapter 1. What is quantum physics? Origins and historical context. Begin lying down or seated in a comfortable position. Let your eyes begin to rest. As your breath slows, your mind will remain just alert enough to absorb the most fascinating subject in all of physics, quantum theory. The true nature of the universe beneath the surface of everyday reality. Part 1. The classical assumptions. Before quantum mechanics emerged, physics was dominated by classical mechanics, established primarily by Isaac Newton in the 17th century. Classical physics assumed objects have definite positions and velocities. Forces act upon masses to determine motion. Energy and momentum are conserved and deterministic. Light is a wave, described by Maxwell's equations. Measurements do not affect the system. But as experiments probed the atomic and subatomic world in the 19th and early 20th centuries, these assumptions began to break down. The first serious crack in classical theory came from the study of blackbody radiation. That's the way objects emit electromagnetic radiation due to temperature. According to classical physics, as an object heats up, it should radiate infinite energy at short wavelengths like ultraviolet light. This became known as the ultraviolet catastrophe. But in reality, hot objects emit finite radiation, peaking at specific wavelengths. Enter Max Planck in the year 1900. To explain this, he made a radical proposal: energy is quantized. Planck introduced the idea that energy could only be emitted or absorbed in discrete amounts called quanta. He defined the energy of a photon, which is a quantum of light, as E equals h times nu. Where E is the energy, h is Planck's constant, 6.626 times 10 to the negative 34 power joule seconds, and nu is the frequency of the radiation. This was the birth of quantum theory. Part 3. Einstein and the photoelectric effect. So 5 years later, in 1905, Albert Einstein used Planck's idea of quantization to explain the photoelectric effect. Classical predictions failed again. Shining light on metal should gradually knock electrons loose regardless of the light's frequency. But instead, electrons were only emitted if the light had a high enough frequency, even if it was dim. Einstein proposed that light is made of particles or photons, each with quantized energy. If the photon energy exceeds a threshold, it can eject an electron. This experiment showed that light behaves as both a wave and a particle. Energy is transferred in packets. The classical wave theory of light was, well, incomplete. Einstein won the 1921 Nobel Prize not for relativity, but for the photoelectric effect. So, another puzzle came from atomic spectra. When atoms are excited, they emit light in discrete lines, not continuous spectra as expected from classical physics. In 1913, Niels Bohr introduced a new atomic model. Electrons orbit the nucleus in quantized orbits. Only specific energy levels are allowed. Light is emitted or absorbed when an electron jumps between levels. His model predicted hydrogen spectral lines with amazing precision. The Balmer series, Lyman series, and others, but it was a patch. It lacked full theoretical justification. Part 5. The birth of quantum mechanics. From 1924 to 1927, modern quantum mechanics was developed. Major contributors during this period included Louis de Broglie in 1924. Louis de Broglie proposed that matter, like electrons, actually has wave-like properties. He introduced the concept of matter waves, suggesting that every particle has an associated wavelength, where p is momentum. Werner Heisenberg in 1925 developed matrix mechanics, which is a formulation of quantum physics based on matrices. Then, in 1926, Erwin Schrödinger developed wave mechanics, which is based on a wave function usually represented as psi that evolves over time. Right. So his famous equation basically describes how a quantum system changes over time. Max Born, he interpreted the absolute value of psi squared as a probability density. Part 6. The core concepts of quantum mechanics. By the late 1920s, the core foundations were in place. The wave function psi describes the quantum state of a system. Superposition means a system can exist in multiple states at the same time. Quantization is where energy and other properties only take on discrete values. Probability, outcomes are inherently probabilistic. Measurement collapse. Observation causes the wave function to collapse. And the uncertainty principle puts limits on how precisely we can know certain pairs of values. All right, so let's take a look at some of the key experiments that really confirmed quantum theory. First up, we've got the double-slit experiment, which started with Young back in 1801, and later was done with electrons in 1961. This one showed quite amazingly that matter has this wave-particle duality. Then there's the photoelectric effect, explained by Einstein in 1905, which proved that light actually behaves like particles. Next, the Davison-Germer experiment in 1927 demonstrated that electrons can diffract just like waves. The Stern-Gerlach experiment from 1922 revealed that spin is quantized, which is pretty wild when you think about it. And finally, the Bell test experiments running from the 1980s all the way up to the 2020s confirmed entanglement and non-locality. These experiments honestly changed the way we see the universe. Part 8. Why quantum theory is so successful. Despite its strangeness, quantum mechanics has passed every experimental test for over a century. It explains atomic structure, chemical bonding, semiconductor physics, lasers, nuclear decay, molecular interactions, and even the structure of stars. And it underpins modern electronics, quantum computing, cryptography, MRI and medical imaging, and all of particle physics. Its predictions are accurate to 14 decimal places, the most precise theory ever tested. Part 9. Interpretations of quantum mechanics. Quantum mechanics is mathematically predictive but philosophically open. Main interpretations include Copenhagen wave function collapse upon observation. Many worlds. All outcomes occur in branching universes. Pilot wave, also known as Bohmian mechanics, deterministic paths guided by a wave. Objective collapse. Collapse is a physical process, not tied to observers. Each predicts the same experimental outcomes but honestly implies very different realities. You've just explored over a century of discovery, from Planck's first step into quantized energy through Einstein's photon theory to the full development of wave mechanics and probability. Quantum physics rewrote the rules of the universe. Now close your eyes. Let the knowledge settle. You've begun the most complete journey through quantum mechanics ever written for sleep. To appreciate the revolution sparked by the double-slit experiment, we must first understand how classical physics viewed the world. In classical terms, matter consists of particles with well-defined paths. Light behaves like a wave described by Maxwell's equations. Objects do not interfere with themselves. So if you take a wall with two narrow slits and fire particles like marbles at it, each particle passes through one slit or the other, landing directly behind. If you fire waves like water or light, the waves pass through both slits, spreading out and interfering. Where peaks meet peaks, they amplify. Constructive interference. Where peaks meet troughs, they cancel. Destructive interference. The result? A ripple pattern on the detection screen. This was all well understood, until someone decided to combine the concepts. The first famous double-slit experiment was done with light by Thomas Young. Set up, a light source shines on a barrier with two narrow slits. Behind the slits is a screen where the light lands. Classical expectation. If light were just particles, it would form two bright spots behind the slits. Actual result? Instead, light created an interference pattern, bright and dark bands. Conclusion: light behaves like a wave, not a particle. This wave behavior was consistent with Maxwell's equations and became the dominant view of light until the early 20th century. In 1905, Einstein showed light also behaves like particles, photons, explaining the photoelectric effect. Here's the dilemma. Light shows interference, a wave property. Light also causes photoelectric emission, a particle property. This duality demanded a new framework. But the true mind-bender would come when we tried the double-slit experiment with particles of matter. In 1961, physicists Klaus Jonsson and others repeated the double-slit experiment, this time with electrons. Electrons are matter, particles. They have mass, charge, spin. One might expect them to behave like marbles passing through one slit or the other, but that's not what happened. When a stream of electrons was sent through the double slits, the screen showed an interference pattern just like waves. Each electron somehow was not behaving like a particle, but as if it passed through both slits simultaneously, interfering with itself. Even more amazing, when electrons were fired one at a time, the pattern still emerged after many electrons built up over time. This behavior was not compatible with any classical concept. So, how can a particle, actually interfere with itself? Quantum mechanics answers this with the concept of the wave function, which is usually denoted by the Greek letter psi. The wave function isn't a physical wave, but rather it's what we call a probability amplitude. If you take psi and square it, that gives you the probability of finding the particle at position x. The way the wave function changes over time is described by the Schrödinger equation. Now, when an electron isn't being observed, it exists in a superposition of all possible paths, meaning, oddly enough, it goes through both slits, not just one. But once you measure which slit it actually goes through, the wave function collapses, and the interference pattern just disappears. Now, imagine adding a detector, say a photon sensor, to see which slit the electron goes through. Suddenly, the electron no longer creates an interference pattern. It behaves like a classical particle. Why is that? Well, because the act of measurement collapses the wave function. By trying to observe which path the particle takes, we basically force it to choose. This is the observer effect, not in some mystical way, but as a fundamental part of quantum theory. In mathematical terms, the wave function psi is altered by interaction with a measuring apparatus, collapsing into a specific eigenstate of the observable, in this case, position. And just to be clear, this has been tested and confirmed in countless experiments. More sophisticated versions of the double-slit experiment, well, they really challenge our intuitions. Take the delayed choice experiment by John Wheeler in 1978. What if you decide after the particle passes the slits whether or not to detect which slit it went through? The result is kind of wild. If you choose to detect, there's no interference. But if you choose not to, the interference returns. Then there's the quantum eraser experiment from 1999. Even after the which path information is detected, if it's erased, the interference pattern reappears. These experiments suggest that information itself determines the outcome, not just physical interaction. Let's recap the conclusions from this one experiment. Particles, like electrons, behave as waves of probability when unobserved. When observed, they behave like particles. Measurement affects the outcome, not just the reporting. The concept of a particle having a definite trajectory is invalid in quantum theory. Future measurements may affect past possibilities as seen in delayed choice. Philosophically, this implies reality is not deterministic, outcomes are probabilistic. Observation creates facts, measurement is not passive. Reality is not fully real until it is measured. Let's briefly touch on the math. The probability of detecting a particle at position x. For a system with two slits A and B, the total wave function is, the resulting probability distribution is, the last term is the interference term, only present if both paths are available and indistinguishable. If which path information is known, the interference term vanishes. This is a statistical mixture, not a quantum superposition. Why does this matter? Because quantum interference is not just a curiosity, it's the foundation of modern technologies. Quantum computing uses interference of qubit states to perform computations. Quantum cryptography exploits measurement effects to guarantee security. Interferometry in gravitational wave detectors uses the same principles. Semiconductor physics, lasers, and MRI all rely on wave function behavior. The double-slit experiment is not just strange, it is essential. One experiment, 2 slits and a screen, revealed that the universe does not behave classically. Particles behave like waves. Observation affects outcome, and probability replaces certainty. As you lie back, eyes growing heavier, let your mind hold one final image, a single electron, alone in the dark, choosing its path only when you decide to look. The next time you think of reality as solid and certain, remember the slits. All right, let's dive right in. Today we're exploring the concept of wave-particle duality, both its mathematical foundation and the real-world proof that backs it up. In the classical worldview, waves and particles are separate entities. Waves are continuous, spread-out phenomena. Think of sound waves or ripples in a pond. Particles are discrete, localized objects. Think of a tennis ball or a planet. But quantum physics shattered this dichotomy. What we learned from early 20th century experiments is this: every quantum object, light, electron, proton, atom, exhibits both wave-like and particle-like behavior depending on how you measure it. This isn't a metaphor, it's a rigorously observed, repeatable fact. In 1924, Louis de Broglie, a French physicist, made a profound suggestion. He proposed, if light, previously thought of as a wave, can behave like a particle, a photon, then maybe particles, like electrons, can also behave like waves. He introduced the matter wave concept. The formula he used to describe the wavelength of a particle is, this suggests, fast-moving particles have shorter wavelengths. Heavy particles have shorter wavelengths. All matter has wave-like properties. This bold hypothesis would soon be confirmed. Just 3 years later, the Davison-Germer experiment verified de Broglie's prediction. The setup was simple yet clever. A beam of electrons was directed at a crystal of nickel. The crystal's atoms acted like a diffraction grating, just like slits in the double-slit experiment. Detectors measured how electrons scattered at different angles. The results were fascinating. The scattered electrons formed interference patterns. This is only possible if electrons behave like waves, not particles. Even more impressive, the wavelength of these electrons matched de Broglie's formula precisely. The conclusion was clear. Electrons have a wavelength. Matter behaves like a wave. This was revolutionary. It unified the behavior of light and matter under a single quantum framework. Let's now look at the other side of duality. In 1923, Arthur Compton studied X-rays scattering off electrons. What he observed contradicted the wave theory of light. X-rays changed wavelength when they bounced off electrons. The change depended on the angle of scattering, kind of like a billiard ball collision. This behavior could only be explained if light acts like a particle, with momentum and energy. The equation that explained this is, well, pretty important. This confirmed photons carry momentum. Light acts like a particle. After de Broglie and Davison-Germer, scientists tested wave-like behavior in larger particles. Molecules, for example. In 1999, researchers demonstrated interference patterns with fullerene molecules, that's 60 carbon atoms arranged in a sphere. Even larger systems are being explored. Modern experiments are investigating interference with proteins, viruses, and potentially even small living systems. The wave-like nature becomes harder to detect as mass increases, because wavelengths get shorter, but theoretically all matter exhibits wave-like behavior. You, reading this, technically have a wavelength. It's just too small to detect. The wave nature of particles isn't a literal ripple on a string. Instead, it is described by the quantum wave function psi, which is a complex mathematical object. The wave function evolves smoothly and deterministically until a measurement is made. Then it collapses probabilistically. Wave-particle duality leads directly into the idea of superposition. In classical physics, an object is in one place at one speed in one state. But in quantum physics, a particle exists in all allowed states simultaneously until measured. This is mathematically represented by adding wave functions, where each term corresponds to a different possible state. Measurement causes the superposition to collapse into one eigenstate, with a probability given by the wave function itself. Quantum objects can show either wave or particle behavior, but not both at the same time. When we talk about waves, we see interference patterns, and the paths are, well, indistinguishable. But when we talk about particles, we're dealing with which path detection and position. The paths become distinguishable. This complementarity is summed up in the Bohr complementarity principle. You can measure wave-like or particle-like behavior, but never both at once. Wave behavior explains another essential quantum feature: quantized energy levels. In atoms, electrons form standing waves around the nucleus. Only certain wave modes fit, just like a guitar string can only vibrate in specific patterns. The allowed wave functions correspond to discrete energy levels. This explains things like atomic emission lines, electron orbitals, and quantum jumps. It's all waves, but of probability, not physical matter. Wave-particle duality raises deep philosophical questions. What is a particle? Is it just a localized detection event? Are quantum objects real before measurement? Is the wave function a tool or a thing? Different interpretations of quantum mechanics provide different answers. In Copenhagen, particles don't have properties until observed. In many worlds, all possibilities exist in parallel branches of reality. In pilot wave theory, particles have defined trajectories guided by a wave. But all agree, quantum objects are not just particles. They are probabilistic waves that become particles upon observation. Wave-particle duality is not just a curiosity, it is a profound feature of all reality. Electrons, photons, atoms, all things behave like waves until observed, then collapse into particles. This is not poetry. This is physics. Now rest your mind. You've learned about the wave-like nature of the universe. Let your thoughts float, like a probability cloud, into dreams. Heisenberg's uncertainty principle, measuring the impossible. In classical mechanics, the position and velocity or momentum of any object can be measured exactly at any moment in time. Knowing those two values allows complete prediction of future motion using Newton's laws. This is determinism, the idea that if you know the initial conditions perfectly, you can predict everything. But in quantum mechanics, there is a hard limit on what you can know about a particle's properties simultaneously. Specifically, the more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. This is not a technological problem, it is a principle of nature. Proposed by Werner Heisenberg in 1927, the uncertainty principle is usually written as, this equation means the more tightly you confine a particle's position, smaller delta x, the more wildly uncertain its momentum becomes, larger delta p, and vice versa. If you try to pin down where something is, you become increasingly unsure of how fast it's moving or where it's going. Alright, let's break this down further. Imagine you've got an electron trapped somewhere. Now you try to spot it by shining some light on it, but see, light isn't just a gentle touch. It's made up of photons. And when one of those photons hits the electron to light it up, it gives the electron a bit of a kick. That kick actually changes the electron's momentum. So, just by figuring out where the electron is, you've gone and changed how it's moving. But, there's more to it than that. Even if you're in complete darkness and not trying to measure anything, the uncertainty principle still holds true. It's not just about interfering with the electron or disturbing it. This uncertainty is baked right into how wave functions work. It comes naturally from the wave-particle duality and, well, the mathematics of quantum waves, specifically the Fourier transform. The uncertainty principle isn't just some made-up rule. It actually emerges from wave theory itself. If you describe a particle with a wave function, let's call it psi of x, then its momentum is tied to the shape of that wave function. This is all about Fourier transforms. If the wave function is sharply peaked in position space, meaning the position is quite well known, then its momentum is spread out, so the momentum is uncertain. On the other hand, if the momentum is tightly grouped, the position wave function is spread out. This isn't just a quirk of quantum physics either. It's a general property of all things that behave like waves. The most famous uncertainty relation is between position and momentum. But there are others. Energy, time, uncertainty. This implies that, well, the shorter the duration of a quantum event, the less precisely you can define the energy involved. Particles can temporarily borrow energy as long as they give it back quickly, which is, a key concept in virtual particles and quantum tunneling. It's important to emphasize the uncertainty principle is not caused by the observer disturbing the system. Even if we had perfect instruments, zero noise, and infinite control, the uncertainty still exists. It's a fundamental feature of quantum reality. There is no such thing as a particle with both an exact position and an exact momentum. This has been tested and confirmed in every modern experiment. Let's explore a real quantum system that minimizes uncertainty. A Gaussian wave packet, which is the most localized, symmetric, and smooth type of quantum state. It turns out the Gaussian wave function provides the lowest possible value for delta x times delta p, satisfying the inequality exactly. These are called minimum uncertainty states, a balance between position and momentum knowledge. Such states are common in coherent light beams, lasers, and in harmonic oscillator ground states like atoms in quantum wells. Uncertainty relations have been observed in various experiments. First, let's talk about electron diffraction. When we try to confine electrons to really narrow slits, the spread of their momentum, well, it increases. As a result, their diffraction angles broaden, just as predicted. Secondly, in the case of optical quantum states, Scientists working in quantum optics labs use light to create states with extremely low position uncertainty. And yeah, they observe that these states have high phase uncertainty. So, let's talk about quantum dots. Electrons trapped inside these tiny nanostructures, well, they show predictable patterns of uncertainty in their energy, position, and momentum. It's a fascinating demonstration of how the quantum world behaves. The uncertainty principle, it really has some deep philosophical consequences. It actually destroys the dream of perfect prediction. First, there's no hidden precision. It's not that we just don't know enough, it's that there isn't an exact value until we measure it. Second, probability is truly fundamental. Quantum physics doesn't describe what is, but rather what might be. Third, there's indeterminism. The future isn't set in stone, it's only probable. And fourth, observer independence. The uncertainty isn't about us or our tools, it's truly baked into the system itself. This isn't a failure of science, it's actually science revealing the true limits of knowledge. But, far from being just a theoretical limitation, the uncertainty principle actually enables a lot of modern technologies. Quantum cryptography, for example, since measurement disturbs the system, it guarantees security. Quantum tunneling lets particles penetrate barriers thanks to energy-time uncertainty. Laser cooling uses momentum uncertainty to trap atoms at almost absolute zero. Electron microscopes, well, they have to balance resolution and disturbance. And semiconductors, they rely on energy-level spacings that come straight from uncertainty. So, that's the end of Chapter 4. You've now encountered a boundary, not a wall, but a principle. You just can't know everything about a system all at once. The tighter you try to focus, the more reality seems to slip away. But that's not chaos, it's actually the delicate balance of nature. Tonight, let uncertainty comfort you. You don't have to know it all. Even the universe can't pin itself down without being asked. So, close your eyes, drift into probability, and rest in the unmeasurable. In classical physics, equations define motion. Newton's second law, F equals ma, tells us how forces affect objects. Maxwell's equations, well, they describe electromagnetic fields. And Einstein's field equations, they lay out gravity and the curvature of space-time. These are dynamical equations. They predict how systems evolve. So in quantum physics, we must ask, what governs the evolution of the wave function psi, which describes a particle's quantum state? This is the time-dependent Schrödinger equation discovered by Erwin Schrödinger in 1926. All right, let's break down the components of the equation. The Schrödinger equation is kind of like Newton's laws for quantum particles, but with waves instead of positions. It tells us this. Given an initial wave function, this equation predicts how it evolves over time. In many practical situations, systems don't change with time, such as, an electron in an atom at rest. In such cases, we use the time-independent Schrödinger equation. This is an eigenvalue equation, where H is an operator acting on functions, psi is the eigenfunction or the wave function, and E is the eigenvalue, which is the allowed energy of the system. Solving this equation gives us the allowed energy levels and the wave functions that correspond to each level. This is basically how we derive them. So, just to give a few examples, you've got the discrete orbits of the hydrogen atom, the energy bands in solids, and, well, the behavior of electrons in quantum wells. The Hamiltonian, often written as H, represents total energy. For a single non-relativistic particle in one dimension, it's defined in a particular way. Here's how it works. The first term is the kinetic energy, described using the second derivative, and the second term is the potential energy, which depends on the particle's position. This equation, basically, turns quantum physics into a differential equation problem, one that you can solve using tools from calculus and linear algebra. Let's solve a classic example using the Schrödinger equation. So here's the scenario. A particle is trapped in a one-dimensional box of length L with walls that are infinitely high. The time-independent Schrödinger equation becomes, well, quite a bit simpler in this case. This result shows quantization of energy. Only certain energies are allowed. And honestly, this is the basis for quantum confinement, which we see in things like quantum dots, semiconductor devices, and atomic orbitals. In 3 dimensions, probably the most famous application of Schrödinger's equation is the hydrogen atom that's just 1 proton and 1 electron. The potential energy here, well, it comes from Coulomb attraction. Solving the Schrödinger equation in spherical coordinates gives us quantized energy levels. Orbital shapes, like s, p, d, and f orbitals, are really the building blocks of chemistry. They're derived directly from the wave function's angular and radial parts. This, you know, explains atomic spectra, periodic table trends, and even chemical bonding. One of the most beautiful features of the Schrödinger equation is superposition. Any linear combination of solutions is also a solution, as long as it's normalized. This leads to quantum interference, beating, and probability oscillations. Over time, each energy component evolves in its own unique way. This time, evolution causes the wave function to change shape over time, kind of like a breathing, flowing pattern of probability. Now, another powerful prediction from Schrödinger's equation is something called quantum tunneling. So, imagine a particle with energy E approaching a barrier of height V, where V is greater than E. Classically, the particle just can't pass, there's not enough energy. But quantum mechanically, the wave function actually penetrates the barrier. And well, there's a non-zero probability that it could emerge on the other side. This idea underlies things like nuclear fusion in stars scanning tunneling microscopes, tunnel diodes, and Josephson junctions. It's a really clear example where the math of the wave function directly predicts a behavior that would be impossible in classical physics. The Schrödinger equation ensures unitarity. Total probability is conserved, that is, at all times. This reinforces the interpretation of as a probability density, the core of Born's rule. The Schrödinger equation keeps the quantum state consistent as it evolves, just like conservation laws in classical mechanics. So the Schrödinger equation is, well, linear, deterministic, and complex valued. It governs a wave function that, contains all possible outcomes. This wave function evolves smoothly, that is, until a measurement occurs, and then at that point the wave function collapses into a single outcome. This dichotomy, smooth evolution versus discontinuous collapse, is, well, absolutely central to the mystery of quantum physics. Some interpretations, like many worlds, remove collapse altogether. Others, like Copenhagen, accept it as part of reality. But no matter the view, all agree. The Schrödinger equation is the engine of quantum behavior. The universe, at its smallest scale, is governed not by force, but by a wave of possibility. Schrödinger's equation is the mathematical hymn of that wave. It does not tell us what is, but what can be, and how those possibilities shift and shimmer through time. Rest now. You've just listened to the universe's most fundamental rhythm. The language of atoms, the law of the invisible, the pulse beneath the surface. Let it carry you into sleep, one evolving wave at a time. In quantum physics, almost every question about particles, forces, or probability leads back to one central entity, the wave function. Represented by the Greek letter psi, it's not just a mathematical convenience, it's the very heartbeat of the quantum world. It is not something we see, touch, or directly observe. Instead, it encodes the probabilities of everything a quantum system might do, from the path of an electron to the spin of a neutron star's particle. And yet, this wave function is so deeply counterintuitive, it defies our classical understanding of reality. Let's take a deep dive, slowly, calmly, into what it is, how it behaves, and why it matters. Imagine a particle. In classical physics, it has a well-defined position and momentum. But in quantum physics, things are hazy, indistinct, uncertain. That uncertainty is described by the wave function. Mathematically, a wave function psi of x and t is a complex valued function that describes the probability amplitude of finding a particle at position x and time t. It doesn't give you answers directly, only probabilities. To get something meaningful from psi, you square its absolute value. This tells us the likelihood of observing a particle at a certain location and time. Let's say an electron can be in state A or state B. In the quantum world, it can also be in both states at once. We write this as this is superposition, where a system doesn't choose a single state until you observe it. Unlike classical physics, where things are either or, quantum mechanics is about and. This principle underlies the double-slit experiment, quantum interference, and qubit behavior in quantum computing. While in superposition, particles can exhibit properties of multiple states, traveling multiple paths, having multiple energies, or spinning in multiple directions at once. The act of observation changes everything. When we measure a quantum system, its wave function collapses into a definite state. Before measurement, it exists as a cloud of probabilities. After measurement, that cloud vanishes, and we see a single outcome. This is wave function collapse. Collapse is non-deterministic. It happens instantly, and we don't fully understand why it occurs. This creates a strange divide. The Schrödinger equation predicts smooth, reversible evolution. Measurement introduces sudden, irreversible collapse. Why does a smooth mathematical function suddenly choose one reality? That's the heart of the quantum mystery. So what causes the collapse? That question has created countless interpretations. For example, the Copenhagen interpretation says measurement causes collapse. The many worlds interpretation, on the other hand, claims there's no collapse at all. All outcomes happen in parallel universes. Then there's decoherence, which suggests collapse is only apparent, not real, and actually comes from interaction with the environment. Bohmian mechanics argues there's no collapse either. Particles just follow hidden paths, guided by a wave. And cubism, well, it says the wave function represents knowledge, not reality itself. Each of these approaches, really changes our understanding of what reality is. So, is the wave function a real physical entity? Or is it just a tool for organizing our knowledge? We honestly don't yet know. But every experiment keeps pointing back to one thing. The wave function is indispensable. When two particles become entangled, their wave functions merge into one inseparable whole. This means measuring one particle affects the state of the other, even if they're light years apart. Entanglement shows us that the wave function doesn't just describe individual particles. It describes relationships between particles across space and time. It creates a kind of non-locality, a deeper connection that seems to bypass the limits of space itself. This is, without a doubt, another reason why wave functions defy classical understanding. Where does the wave function live? Not in regular three-dimensional space, but in something called Hilbert space, an abstract, infinite-dimensional mathematical realm. Each possible quantum state is a vector in this space. Observables like position and momentum are operators that act on these vectors, transforming them and producing measurable outcomes. It's a surreal landscape, really, but in Hilbert space, the rules of quantum logic make perfect sense. Sometimes we don't need to invoke collapse to explain classical behavior. Instead, we can look to decoherence. This is when a quantum system interacts with its environment in such a way that its superpositions become indistinguishable. It's as if the wave function collapsed. But really it just became irreversibly entangled with the environment. While decoherence explains why we don't see superpositions in the macroscopic world, it doesn't explain why only one outcome appears. Still, it's a critical piece of the puzzle, and a bridge between the quantum and classical worlds. Despite its mystery, the wave function is behind nearly every modern technology, semiconductors. Wave function manipulation allows electron flow in microchips. Lasers, coherent wave functions produce synchronized light. MRI machines exploit the quantum states of atomic nuclei. Quantum computing uses superpositions of wave functions or qubits for exponential computation. Quantum cryptography secures data using wave function properties that can't be cloned. Understanding and controlling wave functions is no longer theoretical. It's practical, profitable, and transformational. A final mind-bending question. Is the wave function physically real or merely a reflection of what we know? If it's real, then reality itself is made of probability and possibility. If it's not real, then our measurements shape a deeper unknowable world. Experiments are ongoing, probing deeper into quantum foundations and quantum information theory, but as of today the question remains unanswered. The wave function is not a wave nor a particle. It is possibility, suspended between presence and absence. It is the dream of the universe before awakening into form. It is the quantum hum beneath reality's skin. As you close your eyes and let your breath slow, imagine your thoughts spreading out like a wave function, gentle, infinite, and full of wonder. Rest now, knowing that somewhere in the vast field of probabilities, you are exactly where you're meant to be. Imagine you're at a playground, and you want to get your kickball over a big tall wall. What do you need to do? You need to give that ball a whole lot of energy. You have to kick it really, really hard, so it has enough speed to go up, 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 and over the top. If you don't kick it hard enough, it will go partway up, stop, and fall right back down to your feet. It's a simple rule we see everywhere in our everyday world. This idea is a cornerstone of what we call classical physics, the physics of big things like baseballs, cars, and planets. It's the physics of our direct experience, the stuff that just makes sense. This rule applies to more than just kickballs and walls. Think about a roller coaster. To get up a big hill, the coaster car needs a powerful motor or a long chain to pull it all the way to the top. It needs to gain what we call potential energy. If the motor cuts out halfway up, the coaster doesn't magically appear at the peak. It rolls right back down. In the world we see and touch, you have to pay the energy toll to get over the energy hill. There are no shortcuts, no free passes. Every single time, you must have more energy than the barrier you are trying to overcome. It's a dependable, predictable, and, frankly, quite a sensible rule for how the universe works. Let's take it even further. Consider a marble in a bowl. If you give the marble a little push, It will roll up one side of the bowl and then back down. To get it out of the bowl, you have to give it a push that's strong enough to send it all the way to the rim and over. The rim of the bowl is its energy barrier. Without enough energy to reach that rim, the marble is stuck inside, rolling back and forth forever, if not for friction. This is the classical world in a nutshell. Barriers are absolute. If you don't have the ticket, enough energy, you don't get to ride. It's an unbreakable law for everything big enough for us to see. But what if I told you there's another set of rules? A set of rules that apply to the tiniest things in the universe. Things much, much smaller than a marble, like the atoms and particles that make up everything. For these tiny things, the universe plays by a different, spookier, and much more fascinating set of rules. In this microscopic realm, a particle can find itself on one side of a wall, and then, without ever having enough energy to go over it, suddenly appear on the other side. This is not science fiction. It's a fundamental part of how our universe is built. It's a phenomenon that breaks the classical rules and opens up a whole new world of possibilities. So, how on earth can a particle get through a barrier it doesn't have the energy to cross? It sounds like a ghost walking through a wall, and in a way, that's not a bad way to think about it. In the quantum world, particles like electrons don't just behave like tiny solid balls, they also behave like waves. Think of a ripple spreading out in a pond. This wave-like nature is described by something called a wave function. The wave function is basically a cloud of probability that tells us where we are most likely to find the particle if we were to go looking for it. It's not in one exact spot until we measure it. Now, let's go back to our energy barrier, our wall. For a quantum particle, its wave function doesn't just stop dead when it hits the wall. Instead, the wave gets a lot smaller. It dampens as it goes into the barrier. But here's the amazing part. The wave doesn't completely disappear inside the wall. A tiny, tiny little bit of that wave can actually leak all the way through to the other side. It's like hearing a muffled sound from the next room. Most of the sound wave is blocked by the wall, but a little bit still makes it through to your ears. This is what a particle's wave function does. Because a tiny part of the wave function makes it to the other side of the barrier, it means there is a small, but not zero, probability that if you go to look for the particle, you'll find it there. It didn't break the wall down. It didn't borrow energy to climb over it. It just appeared. This is quantum tunneling. The particle has a chance of being found on the far side of the barrier, having tunneled through a region that should have been completely forbidden according to classical physics. The universe, at its most fundamental level, allows for these seemingly impossible journeys. The whole thing is based on probability. It's not a sure thing. Most of the time, the particle will hit the barrier and bounce right off, just like our classical kickball. But every so often it tunnels through. The chance of this happening depends on the barrier itself. If the wall is very thick or very high, the wave function shrinks to almost nothing inside it, and the probability of tunneling becomes incredibly small. But if the barrier is thin enough, tunneling becomes not just possible, but a regular and predictable occurrence in the quantum realm. It's a ghost in the machine of the universe. You might be thinking, okay, this is some weird abstract science stuff that happens in a lab, but quantum tunneling is happening all around us and even inside of us all the time. It's essential to the universe as we know it. Take the sun, for example. The sun shines because of nuclear fusion, where hydrogen atoms are smashed together to make helium, releasing a tremendous amount of energy. But there's a problem. The protons in the hydrogen atoms are all positively charged, and like charges repel each other. The core of the sun is incredibly hot, but it's still not hot enough for the protons to have enough energy to slam into each other directly. So how does fusion happen? You guessed it, quantum tunneling. Even though the protons don't have enough energy to overcome their mutual repulsion, their wave functions can leak through that energy barrier. This allows two protons to get close enough for a different force, the strong nuclear force, to take over and fuse them together. Without quantum tunneling, the protons in the sun would just bounce off each other. There would be no fusion, no sunlight, no heat, and no life on Earth. The very fact that our star shines is a daily testament to the power of this quantum phenomenon. Tunneling is also at the heart of modern electronics. Consider a device called a tunnel diode, found in things like oscillators and amplifiers. It uses a special junction between two types of semiconductor materials. Classically, electrons shouldn't be able to cross this junction without a big energy push. But thanks to tunneling, Some electrons can slip right through the energy barrier, creating a current. This allows for incredibly fast switching speeds that are essential for high-frequency electronics. Another amazing device, the Scanning Tunneling Microscope, or STM, uses tunneling to see individual atoms by measuring the flow of electrons tunneling between a sharp metal tip and a surface. Even something as fundamental as radioactive decay relies on tunneling. In the nucleus of a heavy, unstable atom like uranium, there are clusters of particles called alpha particles. These particles are trapped inside the nucleus by the powerful, strong nuclear force, which acts like a very high-energy wall. The alpha particle doesn't have enough energy to break out, but its wave function leaks through the barrier, and eventually, there's a chance it will tunnel out of the nucleus. When it does, we call that alpha decay. Quantum tunneling explains why radioactive elements have predictable half-lives. It's all about the probability of a particle making that impossible escape. One of the most mind-boggling things about quantum tunneling is how incredibly sensitive it is to the barrier it's trying to cross. We're not talking about a small effect here. We're talking about massive changes in probability based on the tiniest changes in distance or energy. The relationship is what scientists call exponential. This means that if you make the barrier just a little bit thicker, the chance of a particle tunneling through doesn't just go down a little bit, it plummets. It might become 1,000,000, 1,000,000,000, or even 1,000,000,000,000 times less likely. It's like trying to whisper through a wall. Adding even one more brick makes a huge difference. This extreme sensitivity is not a bug. It's a feature. It's what makes the Scanning Tunneling Microscope, or STM, so unbelievably precise. The STM works by positioning a needle-sharp tip just a few atoms away from a surface. A small voltage is applied, and electrons begin to tunnel from the tip to the surface, creating a tiny electrical current. Because the tunneling probability is so sensitive to distance, if the tip moves closer to the surface by the width of a single atom, the tunneling current increases dramatically. By keeping this current constant, the microscope can map out the bumps and valleys of a surface with atomic resolution. Think about it this way. Imagine you are trying to throw a piece of paper through a closed window. Impossible, right? Now imagine the window is ever so slightly open, just a crack. Maybe 1 in a trillion throws will get through. Now if you open that crack just a tiny bit wider, maybe your chances improve to 1 in a million. A tiny change in the barrier, the width of the crack, led to a huge change in the outcome. That's the power of exponential sensitivity. The wave function inside the barrier fades away so fast that even a minuscule increase in the barrier's thickness is enough to virtually extinguish it. This same principle governs the rate of nuclear fusion in stars and the speed of certain chemical reactions. The energy barrier that protons must tunnel through in the sun is just right. If it were slightly higher or wider, tunneling would be so rare that the sun wouldn't ignite. If it were slightly lower or thinner, fusion would happen so fast that the sun would have burned out billions of years ago. The delicate balance of our universe, from the atomic scale to the cosmic scale, relies on this knife-edge sensitivity of quantum tunneling. It's a game of angstroms where the smallest change makes all the difference. So quantum tunneling isn't just for physics and electronics. It actually plays a subtle but critical role in the machinery of life itself. In the fields of chemistry and biology, scientists are discovering that, well, nature has been using this quantum trick for billions of years. Many chemical reactions, especially those happening inside living cells, involve moving particles like protons or electrons from one molecule to another. Often this requires overcoming an energy barrier, kind of like our kickball needing to get over the wall. But sometimes, that barrier is just too high for the reaction to happen at the speed life requires. Now this is where enzymes come in. Enzymes are these amazing biological catalysts that speed up chemical reactions. For a long time, scientists believed they worked simply by lowering the energy barrier, like giving the kickball a ramp to go up, and they do. But research now shows that for some reactions, especially those involving the transfer of light particles like hydrogen, enzymes also work by making the barrier thinner. By precisely holding molecules in place, an enzyme can shorten the distance a proton needs to travel, dramatically increasing the probability that it will just tunnel right through. This allows reactions to happen millions of times faster than they would otherwise. Let's consider photosynthesis, the process plants use to turn sunlight into energy. It involves a chain of reactions where energy, in the form of an excited electron state called an exciton, has to jump from one molecule to the next. This process needs to be incredibly efficient and fast before the energy is lost as heat. Some scientists believe that quantum tunneling helps these excitons hop between molecules with near-perfect efficiency, navigating the complex molecular landscape of the plant cell. The energy doesn't have to climb over every barrier. It can tunnel through, finding the quickest path to where it's needed. Even our own DNA might not be immune to the effects of quantum tunneling. DNA is held together by hydrogen bonds, where protons sit between two larger molecules. There's a small but real probability that one of these protons could tunnel from its normal position to a different one, changing the structure of the DNA base. This could lead to a mutation, a change in the genetic code. While this is likely a very rare event, it actually shows how quantum phenomena can have profound consequences, potentially driving genetic variation and evolution over millions of years. So, life, it seems, operates on both classical and quantum principles. It's easy to hear about quantum tunneling and think that it's breaking some fundamental laws of physics. If a particle gets to the other side of a barrier without having enough energy, didn't it get something for free? This is a common point of confusion, but tunneling does not violate the law of conservation of energy. This law states that energy cannot be created or destroyed. When a particle tunnels through a barrier, it doesn't gain any energy in the process. If it starts with a certain amount of energy on one side, it will have the exact same amount of energy when it appears on the other side. The key is to remember the wave-like nature of particles and the Heisenberg uncertainty principle. This principle tells us there's a fundamental limit to how well we can know certain pairs of properties at the same time, like a particle's position and its momentum, or its energy, and for how long it has that energy. For a very, very short period of time, a particle's energy can be uncertain. This brief uncertainty might allow the particle to borrow just enough energy to overcome the barrier, as long as it pays it back almost instantly. This is one way to think about it, but the most accurate view is through the wave function. The main difference between tunneling and classical transport is not about energy, but about certainty versus probability. In the classical world, the outcome is certain. If the ball doesn't have enough energy, it will never get over the wall. The probability is zero. In the quantum world, the outcome is probabilistic. The particle's wave function gives it a certain chance of being found on the other side. It's not guaranteed to tunnel. In fact, it's usually very unlikely. But unlikely is not the same as impossible. The laws of quantum mechanics don't break the rules of energy conservation. They just introduce a new element of chance and possibility. So, tunneling isn't a magic trick. It's a direct and measurable consequence of the probabilistic rules that govern the subatomic world. The particle isn't cheating the system. Instead, the system itself has rules that are different from the ones we're used to. It's like discovering that in a certain game, you don't always have to go around an obstacle. Sometimes the rulebook allows you to go straight through it. The rules are still being followed. They're just not the rules you initially expected. Quantum mechanics rewrites the rulebook for the very small, and tunneling is one of its most fascinating chapters. If a particle can tunnel through a barrier, a natural question to ask is, how long does it take? This question has puzzled physicists for decades because it's surprisingly tricky to answer. If you try to measure the time it takes for a particle to travel from one side of the barrier to the other, you run into some strange and counterintuitive results. Some early calculations and experiments suggested that the tunneling process could happen faster than it would take light to travel the same distance across the barrier. This idea is known as the Hartmann effect, and it caused a lot of excitement and confusion. Could this mean that quantum tunneling allows for faster-than-light communication, breaking one of the most fundamental rules of Einstein's theory of relativity? The short answer is no. While the Hartmann effect is a real, observable phenomenon, it doesn't actually violate causality or the universal speed limit. The confusion arises from how we define the speed of a tunneling particle. We're talking about the peak of a wave packet, but that peak doesn't carry any new information. The front edge of the wave packet, which is what would carry a signal, never travels faster than light. Think of it like a long train entering a tunnel. If the train is very, very long, the front of the train might still be entering the tunnel at the same moment the middle of the train is exiting. It might seem like the middle of the train traveled through the tunnel instantaneously, but the information, the arrival of the train itself, was still limited by the speed of the engine at the front. The Hartmann effect is a bit like that. The peak of the probability wave is reshaped as it passes through the barrier, making it seem like it got there impossibly fast, but no information or matter actually breaks the cosmic speed limit. So, while the question of tunneling time is a deep and active area of research with no single simple answer, we can be confident about one thing: it doesn't break physics. The universe's fundamental traffic law, nothing with mass can travel at or faster than the speed of light, remains intact. Quantum mechanics might be weird, but it's not lawless. The spooky-sounding results from tunneling time experiments highlight the challenges of applying our everyday concepts of time and speed to the bizarre, probabilistic world of quantum particles. It shows us there is still so much more to learn. Quantum tunneling is so strange that it has inspired a lot of myths and misconceptions, especially in science fiction. The most popular one is the idea that if quantum tunneling is real, then you should be able to walk through a solid wall. After all, you're made of quantum particles, right? While it's true that you are made of atoms and the particles in those atoms can tunnel, the probability of all of them tunneling in the same direction at the exact same time is so astronomically small that it's practically zero. It's not just unlikely, it's mind-bogglingly, universe-endingly unlikely. To put it in perspective, the probability of a single electron tunneling is already small. Now consider that your body contains an absurd number of particles, something like 10 to the power of 28. For you to walk through a wall, every single particle in your body would have to tunnel through the wall's barrier simultaneously. The chance of this happening is so low that if you stood in front of a wall and tried to walk through it for the entire age of the universe, it would still, for all practical purposes, never happen. So please don't try running into walls. Classical physics is still very much in charge at our scale. Another common myth, fueled by the Hartman effect we just discussed, is that tunneling allows for faster-than-light travel or communication. As we saw, this isn't the case. While some interpretations of tunneling time can seem paradoxical, no experiment has ever shown information being transmitted faster than light. The fundamental principles of relativity hold firm. Tunneling is a consequence of quantum probability, not a loophole in causality. It doesn't let you send a message back in time or instantly across the galaxy. It's a local, probabilistic event that respects the universe's ultimate speed limit. Finally, there's the misconception that tunneling violates energy conservation, which we've already addressed. It's worth repeating. The particle on the other side of the barrier has the same energy it started with. The weirdness of quantum mechanics doesn't lie in breaking established conservation laws, but in revealing that reality is governed by probability waves, not by the deterministic certainty of classical mechanics. Tunneling is not magic. It's just a beautiful and counterintuitive consequence of the quantum rules that have been there all along, governing the hidden world beneath our own. From the fiery heart of our sun to the delicate dance of enzymes in our cells, quantum tunneling is a fundamental process that shapes the universe. It's not an obscure footnote in a physics textbook. It's a headline story about how reality works. It bridges the gap between the impossible and the possible, allowing nature to perform feats that would be forbidden by the common-sense rules of our everyday world. Without tunneling, stars wouldn't shine, many chemical reactions essential for life would grind to a halt, and the elements that make up our planet might not even exist in their current abundances. The impact of tunneling on technology is just as profound. Our entire digital world, with its powerful computers and high-speed communication networks, is built on semiconductor devices that exploit quantum effects. Tunnel diodes, flash memory, and Josephson junctions in superconductors are all direct applications of our understanding of quantum tunneling. The scanning tunneling microscope didn't just give us a new tool, it opened our eyes to the atomic landscape, allowing us to see and manipulate individual atoms for the first time, paving the way for the field of nanotechnology. Beyond its practical applications, quantum tunneling forces us to confront the deep and mysterious nature of reality. It challenges our intuition and reveals a universe that is far stranger and more wonderful than our classical senses would have us believe. It shows that at the most fundamental level, the universe is a place of probability and potential, not just of mechanical certainty. Studying tunneling pushes the boundaries of our knowledge, raising deep questions about time, causality, and the very meaning of a particle's existence. It is a constant reminder that there is always more to discover. So, the next time you look up at the sun, use your smartphone, or just think about the intricate chemistry that keeps you alive, give a little nod to quantum tunneling. This ghostly leap through forbidden barriers is a perfect example of how science reveals a hidden layer of reality, one that is beautiful, powerful, and essential to everything we know. It's a testament to the fact that the universe is full of wonders, and by using science, we can begin to understand them. It's not magic, it's something much, much cooler. It's physics. In our everyday world, things feel wonderfully predictable. If I drop a pen, it falls. We know exactly where the Earth will be in its orbit around the Sun a year from now. This is the world of classical physics, a clockwork universe where if we know enough about the present, we can calculate the future with astonishing precision. It is a world of certainties, of causes leading to definite effects. For centuries, we thought this was the fundamental nature of reality itself. But as we began to explore the universe at its smallest, most intimate scales, we discovered something profoundly different, something that shook the very foundations of what we thought we knew. Down there, in the realm of atoms and electrons, the universe seems to play by a completely different set of rules. The rigid certainty we take for granted simply melts away. It is replaced by a world governed not by definite outcomes, but by probabilities, by chance, by maybes. An electron isn't in one specific place. It exists in a cloud of possibilities. This isn't because our instruments aren't good enough to pin it down. It's because at its core the universe itself is uncertain. It's a beautifully strange idea that the fundamental language of nature is not one of absolute statements, but of statistical likelihoods. This is a very different kind of probability to what we're used to. Think of flipping a coin. We say there is a 50-50 chance of heads or tails, but that is really just a statement about our own ignorance. If we knew the exact force of the flip, the air currents, the spin, and the surface it lands on, we could, in principle, predict the outcome every single time. The probability here is a shortcut, a way of dealing with incomplete information. It's a reflection of what we don't know. But in the quantum world, probability is not a shortcut. It is the real story. The universe, at this fundamental level, does not seem to have decided which outcome to choose until the very last moment. It's as if nature itself is constantly weighing up different possibilities, holding them all in a delicate balance. The chance isn't in our knowledge. It is woven into the very fabric of reality. This shift from a deterministic world to a probabilistic one is one of the most significant and mind-bending discoveries in the history of science. It forces us to rethink what it means to know something, and what it means for something to be real. To get a feel for this, let's imagine a quantum coin. A normal coin can only be heads or tails. When it's spinning in the air, it's still one or the other, we just don't know which yet. But a quantum coin can be in a state called superposition, which means it is both heads and tails at the same time. It's not a 50-50 mix. It's a genuine combination of both possibilities existing simultaneously. This state contains all the potential outcomes, held together in a sort of suspended reality. It's a concept that has no direct parallel in our large-scale world, a truly ghostly and beautiful state of being. So, how do we get a definite answer? We have to make a measurement. In our example, this is like catching the quantum coin and looking at it. The very act of observation forces the universe to make a choice. The superposition collapses, and the coin instantly becomes either heads or tails. But which one? Well, that is where probability comes in. We can't predict the outcome of a single measurement with certainty. We can only state the odds. For our quantum coin, the rules might say there is a 50% chance of heads and a 50% chance of tails. Before we look, it's both. After we look, it's one. The mathematics behind this is both elegant and strange. We don't just assign a probability to each outcome. Instead, we use something called a probability amplitude. You can think of this as a sort of deeper probability, a number that can be positive, negative, or even complex. To get the actual probability we see in an experiment, we have to take this amplitude and square it. This simple mathematical step is known as the Born rule, and it is the crucial link between the strange, hidden quantum world of amplitudes and the measurable, probabilistic world we can observe in our laboratories. A quantum state, then, is like a complete list of all possible outcomes for a measurement. each with its own probability amplitude. For an electron, its state might describe the probability of finding it here or there or over there. The important thing is that when you square all the amplitudes to get the real probabilities, they must all add up to 1 or 100%. This just means that the electron has to be found somewhere. The universe might be built on chance, but it's not completely lawless. Certainty is gone, but the rules of probability provide a new kind of order. Here is where quantum probability becomes even stranger than a simple coin toss. Because probability amplitudes are not just simple numbers, they can behave like waves. And just like waves in the ocean, they can interfere with each other. Two waves can meet and add up, creating a bigger wave. Or, wonderfully, they can meet and cancel each other out completely. This means that quantum probabilities can do something classical. Probabilities can't. They can subtract. You can have a situation where a particle has a chance of going one way and a chance of going another. But if you allow both paths, the probability of arriving at a certain point can become zero. The most famous demonstration of this is the double-slit experiment. If you fire tiny particles like electrons, one by one at a screen with two narrow slits in it, you might expect to see two simple bands on the detector behind it, right where the electrons pass through. But that's not what happens. Instead, you see a complex pattern of many bands, a pattern of interference. It's as if each single electron, traveling on its own, passes through both slits at once. Its two possible paths, represented by probability waves, interfere with each other. In some places on the detector screen, the probability waves from each slit arrive in sync. They add up, and you get a bright band, a high probability of finding the electron there. In other places, the waves arrive out of sync. The peak of one wave meets the trough of the other, and they completely cancel out. At these spots, the probability of an electron ever landing becomes zero, creating a dark band. This is extraordinary. The mere existence of a second path that the electron could have taken changes the probability of where it ends up. This wave-like nature of chance is a fundamental feature of the quantum world. It tells us that we cannot think of an electron as a tiny billiard ball following a single definite path. We must think of it as a wave of possibility, exploring all available routes simultaneously and interfering with itself along the way. The final pattern we see on the screen is a physical manifestation of these hidden probability waves. It is a beautiful, visible map of the quantum rules of chance, showing us a reality far more interconnected and mysterious than we ever imagined. This inherent uncertainty in the quantum world leads to one of its most famous and profound consequences, the Heisenberg uncertainty principle. Now, this isn't a statement about the limits of our technology. It's a fundamental limit imposed by nature itself. What it says is that there are certain pairs of properties that we can never know with perfect accuracy at the same time. The most well-known pair is a particle's position and its momentum, that is, where it is and where it's going. The more precisely you measure one, the less precisely you can possibly know the other. Imagine trying to measure the exact position of an electron. To see it, you have to interact with it, perhaps by bouncing a particle of light, a photon, off it. But an electron is so tiny that even a single photon gives it a significant kick, changing its momentum in a way you can't perfectly control. If you use a high-energy photon to get a very precise measurement of its position, you give it a huge, unpredictable kick, making its momentum very uncertain. If you use a low-energy photon to be gentle with its momentum, its long wavelength means you only get a fuzzy idea of its position. This trade-off is built into the wave-like nature of quantum particles. A particle with a very specific, well-defined momentum is like a perfect, infinitely long wave. But where is it? A wave that stretches on forever doesn't have a specific location. To give it a location, you have to add many different waves together to make them cancel out everywhere, except in one small region. But now that it's made of many waves, it no longer has one specific momentum, it has a whole range of them. You have traded certainty in momentum for certainty in position. This principle has deep philosophical implications. It means that at a fundamental level, reality is fuzzy. A particle doesn't have a precise position and a precise momentum waiting to be discovered. The very concepts of precise position and precise momentum cannot coexist for the same particle. This has led to debates that continue to this day. Some physicists, like Einstein, were deeply uncomfortable with this, believing that the probability was still a sign of an incomplete theory. He famously said, "God does not play dice." But for many others, the evidence suggests that the universe really does operate on chance. While these ideas might seem abstract and philosophical, the probabilistic nature of the quantum world is not just a curiosity. It is the engine behind some of the most advanced technologies we are developing today. By harnessing the strange rules of superposition and probability, we are learning to build machines that were once the stuff of science fiction. Quantum mechanics isn't just about describing the universe. It's about using its deepest rules to change our world in remarkable and powerful ways. The maybes of the quantum world are giving rise to the certainties of future technology. Quantum computers are perhaps the most famous example. A classical computer bit is either a 0 or a 1. A quantum bit, or qubit, can be in a superposition of both 0 and 1 at the same time. By linking many qubits together, a quantum computer can explore a vast number of possibilities simultaneously, performing calculations that would take a classical computer billions of years. This power comes directly from embracing the idea that multiple outcomes can exist at once. It turns quantum fuzziness from a limitation into an incredible resource for computation. Quantum probability also offers a new way to secure our communications. Quantum cryptography uses the principle that measurement disturbs a quantum system. If two people share a secret key encoded in the quantum states of photons, any attempt by an eavesdropper to intercept and measure the photons will inevitably change them. This change can be detected, revealing the presence of a spy. The security is guaranteed not by a clever code, but by the fundamental laws of quantum physics and probability. The uncertainty principle itself becomes our guardian. From ultra-precise sensors that can detect tiny gravitational shifts to new forms of medical imaging like MRI, the fingerprints of quantum probability are everywhere. These technologies work because we understand the probabilistic rules that govern atoms and their nuclei. We have learned to speak nature's language of maybes. And so, we find ourselves in a universe that is far less predictable than we once thought, but perhaps far more interesting. At its heart, reality is not a story that has already been written. It is a shimmering, beautiful, unfolding story of possibilities. Breathe in and out. Let the stillness of the cosmos surround you. Tonight, I want to take you to the quietest place imaginable, the quantum vacuum. But here's the twist: in this realm of apparent nothingness, we find everything. Let's start with the old idea of nothing. Classical physics painted the vacuum as pure emptiness. No matter, no energy, just blank space. But that's not how quantum physics sees it. In this world, emptiness is a myth. The vacuum isn't silent. It's alive, humming with invisible activity. Even when there's no matter or radiation, the quantum vacuum boils with spontaneous fluctuations. These aren't just mathematical quirks. They're real, measurable, and crucial to the very fabric of our universe. Early scientists imagined the vacuum as a perfect void. But quantum mechanics tells a different story. Because of Heisenberg's uncertainty principle, no quantum field can ever be totally at rest. Instead, it jitters with tiny temporary bursts of energy. Picture it, a restless sea, with particles popping in and out of existence, even in total darkness. Why is that? It's all because of zero-point energy, the lowest energy a quantum system can have. Even at absolute zero, with all classical motion stopped, quantum systems still vibrate with this irreducible energy. Imagine a mass on a spring. Classical logic says at zero energy, it just sits there. But quantum logic says, not so fast. That particle must always wiggle, even if just a little. So every quantum field holds a baseline hum of energy, even when empty. And those jittery disturbances, they're often described as virtual particles, particle-antiparticle pairs that flicker into existence, borrow energy from the vacuum and vanish before you can catch them. They're not quite real in the everyday sense, but their effects definitely are. For example, there's the Casimir effect. Put two metal plates close together in a vacuum, and quantum field theory says they'll actually attract. Not because of static electricity, but because the vacuum between them is different from the space outside. This difference creates pressure, pushing the plates together. And yes, we've actually measured this. It proves the vacuum isn't empty. It's packed with dynamic energy. Quantum field theory takes this even further. Every particle you know, electrons, photons, quarks, is just a ripple in a field that stretches across all of space. Even when there are no ripples, the field itself vibrates, generating zero-point energy. So, the vacuum is never truly empty. It's the stage on which all reality dances. And here's where it gets really wild. The vacuum might help us understand dark energy, the mysterious force accelerating the universe's expansion. If the vacuum contains energy, it could explain this cosmic push. But here's the catch: quantum theory predicts way more vacuum energy than we actually observe. Like 10 to 120 times more. That mismatch is one of physics' greatest puzzles. But the vacuum isn't just energetic, it's structured. Sometimes it even breaks symmetry, giving rise to particles and forces. This is how the Higgs field works. As particles move through it, they pick up mass. So even mass itself is a gift from the vacuum. In the earliest moments after the Big Bang, quantum fluctuations in the vacuum were stretched out, seeding galaxies, stars, and planets. Without this restless background, there would be no cosmic structures at all. Maybe not even us. Now, could we ever tap into this ocean of vacuum energy? Science fiction loves the idea, but reality is a lot more stubborn. Extracting energy from the vacuum is, as far as we know, impossible. Still, the quest to understand it pushes the boundaries of what's possible in physics. So as you settle into sleep, remember, the universe's quietest places are secretly teeming with possibility. In the heart of emptiness, something is always waiting to become everything. Close your eyes. You are in a quiet room. A box sits in front of you. You don't know what's inside, only that something may be alive, or not. Yet, until you look, it is both. Tonight, we open the box, not to reveal an answer, but to understand the question. In 1935, the Austrian physicist Erwin Schrödinger proposed a thought experiment that still haunts and challenges our understanding of the quantum world. Imagine a cat placed in a sealed box. Inside the box, a radioactive atom has a 50% chance of decaying within an hour. If it decays, a Geiger counter detects it, triggering a hammer. The hammer shatters a vial of poison gas. The cat dies. If the atom does not decay, the cat remains alive. According to quantum mechanics, before the box is opened, the atom exists in a superposition. It has both decayed and not decayed. So what about the cat? Is it alive? Is it dead? In quantum terms, the cat must also be in a superposition, both alive and dead, until observed. This simple yet eerie scenario opens the door to profound philosophical and scientific questions about the nature of reality, observation, and consciousness. Let's begin with the core idea behind Schrödinger's cat superposition. In quantum physics, particles do not occupy a single state. Instead, they exist in a combination of all possible states until measured. An electron can be spinning clockwise and counterclockwise, in two different locations, in two energy states at once. Only when we observe or interact with the particle does the superposition collapse into a definite state. It's as if reality is not fixed until we look at it. This behavior is confirmed by countless experiments, most famously the double-slit experiment, where particles behave like waves until observed and like particles when watched. Schrödinger's cat was meant to illustrate the absurdity of applying quantum rules to everyday objects. He wasn't saying cats are actually both alive and dead. He was critiquing the idea. But today, We know that macroscopic superpositions may not be as absurd as once thought. Scientists have created superpositions in large molecules with thousands of atoms, superconducting circuits used in quantum computers, mechanical resonators, tiny mirrors that vibrate in multiple places at once. These experiments suggest that quantum weirdness might not stop at the atomic scale. It just gets harder to detect because of decoherence. Why don't we see cats in superpositions in daily life? Well, the answer lies in quantum decoherence. When a quantum system interacts with its environment, it rapidly loses its quantum coherence. The system becomes entangled with everything around it, and the delicate superposition appears to collapse into a single classical state. In the case of the cat, the air molecules, photons, and heat inside the box all interact with the system. These interactions effectively measure the state long before any human opens the box. So the cat is effectively either dead or alive, not both, for all practical purposes. Decoherence, in this way, bridges the gap between quantum possibility and classical reality. A central question in quantum physics remains, when does a superposition collapse? There are several competing interpretations. First, the Copenhagen interpretation: the wave function collapses upon measurement. Observation plays a central role, but what exactly counts as a measurement? Second, the many worlds interpretation: the wave function never collapses. Instead, all outcomes happen in separate branching universes. In one, the cat lives. In another, it dies. You are entangled with each version in a different universe. Third, the consciousness causes collapse idea: the wave function collapses only when a conscious observer becomes aware. This implies a deep link between mind and matter. And fourth, objective collapse. Models collapse happen spontaneously under specific conditions. It doesn't require observers. It's a built-in physical process. Each interpretation, makes identical predictions for most experiments, yet their philosophical implications are radically different. One of the most unsettling ideas in quantum physics is the notion that observation affects reality. Does reality wait for us to observe it? Are we creating the outcomes we see? Or are we merely selecting one branch of an existing multiverse? In Wheeler's delayed choice experiment, the behavior of particles seems to depend on choices made after they travel, challenging our very understanding of time and causality. It suggests that present actions can influence the past behavior of particles, at least from a quantum perspective. This idea, while deeply counterintuitive, is backed by rigorous experiments. Some interpretations link consciousness directly to wave function collapse. While, this is a bit controversial, the idea has fascinated physicists, philosophers, and mystics alike. Could it be that consciousness is not just observing reality but actively shaping it? Roger Penrose and Stuart Hameroff have proposed the orchestrated objective reduction, or OR theory, suggesting that consciousness arises from quantum processes in brain microtubules. While speculative and often debated, the theory reflects a growing curiosity about how mind and matter might be intertwined at the quantum level. Whether or not consciousness causes collapse, it's clear that observers matter in the quantum world. Schrödinger's cat also invites us to reflect on choice and free will. If the universe branches into all possibilities, and each version of you follows a different path, what does that mean for your decisions? Are you choosing, or are you simply experiencing one possible outcome? If everything that can happen does happen, is there meaning in choice? Quantum mechanics doesn't give clear answers, but it asks beautiful questions. Ultimately, Schrödinger's cat is a metaphor, not just for quantum mechanics, but for life itself. We all live in a kind of superposition, filled with potential, hovering between paths not yet chosen. Until we act, until we observe, we are more than one thing. We are possibilities. In every moment, we are both the cat and the observer. Sleep recap, holding paradox, gently. There is a cat in a box. You do not open it. You do not know. Yet in your not knowing you hold both truth and possibility. Quantum mechanics invites us to rest in uncertainty and trust the richness of potential. As you close your eyes, imagine the box. Let it stay closed. Let its mystery be complete. The cat is alive. The cat is not. And you are the observer, floating gently in between. Let this thought drift through your mind like a quiet particle, neither here nor there. You are quantum. You are peaceful. You are many things at once. Sleep now and collapse softly into one. Close your eyes. You are standing on a path. Ahead of you, the road splits. One fork turns left, one goes right. But then, something strange. You walk both. In one version of the world, you choose one direction. In another, the other. Both are real. Both are you, and neither of you knows about the other. For decades, physicists grappled with a strange question. If particles exist in a superposition of possibilities, why do we only see one outcome? In the classic Copenhagen interpretation, the answer was simple but unsettling. The act of measurement collapses the wave function. Everything reduces to a single result. The others vanish. But in the 1950s, a young physicist named Hugh Everett III asked, what if nothing collapses at all? What if all the possible outcomes actually happen? Thus was born the many worlds interpretation, one of the most fascinating and honestly sleep-worthy ideas in all of science. Everett proposed that when a quantum system branches into multiple possibilities, say a particle spins up or down, the universe itself splits. Each possible outcome is realized in a separate, parallel branch of the universe. In one branch, the electron spins up. In another, it spins down. In one, you get the job. In another, you don't. And in each world, a version of you continues living, unaware of the others. You are not a single path. You are a tree of paths, endlessly branching. This idea is not science fiction. It's a real interpretation of quantum mechanics taken seriously by many physicists, including Sean Carroll, David Deutsch, and Max Tegmark. In the many worlds view, every quantum event that could go multiple ways does. Your every decision, or even every particle interaction, leads to a split, a sneeze, not sneezed, a coin flip, heads and tails, a word spoken and not spoken. Every outcome exists. Every choice branches a new you. You are both the chooser and the chosen. Now you may ask, if we can't observe these other worlds, how can we be sure they're real? That's the paradox. Many worlds makes the same predictions as other interpretations, but removes the need for collapse. Instead of saying the wave function collapsed into this one reality, it says, well, you are now in one of many realities. And while we can't visit the others, the math works without mystery. Some physicists prefer this for its elegance. There is no special observer, no magic collapse, no exceptions to the rules. Just an ever-branching universe, pure and complete. What does it mean for you if every possible version of you already exists? This idea touches not just on physics, but on identity, free will, and consciousness. In this view, every decision you might have made, you did make in some other world. Every life you could have lived, you are living somewhere. Every moment is a branching of selves. This may feel overwhelming or freeing. It suggests that you are not one thing but many. Somewhere another version of you is sleeping under alien stars, playing piano instead of guitar, saying yes instead of no, and all of them are equally real. Imagine this as a dream. You walk through a quiet forest. The trees stretch infinitely high. But every tree is not a tree. It's a timeline. Each branch is a world. Each leaf a version of you. You sit under a tree and close your eyes. You drift, and the leaves begin to fall, slowly and softly. Each leaf lands as a choice, a story, a world. And none are wrong, none are lost, none are discarded. The universe does not choose, it keeps everything. If there are infinite versions of you, then who are you right now? This moment, this version of consciousness is a snapshot among billions. You are the you who clicked this video. The you who wants to sleep while learning about quantum possibility. The you who wonders gently about how big everything really is. That version matters, even if there are others. You may be one leaf, but the tree is vast because you exist. And your experience, or your thoughts, your rest, echo through countless branches. Some interpretations of many worlds suggest even more strange implications, that you can time travel by branching into the past, that every interaction with quantum systems is like a vote on reality, that memory itself may be quantum, and when you forget something, perhaps some part of you remembers it elsewhere. While these ideas remain theoretical, they provoke deep, strange comfort. That we are not isolated in the vastness, that we exist in a family of infinite selves, that no path is truly lost, only walked by another you. Breathe in slowly and exhale. Let yourself imagine now, just for a moment, that every version of you is at peace. The you who left early, the you who stayed late, the you who reached out, the you who stayed silent. Each one is simply walking their path. You do not need to hold every choice. You only need to rest in the knowledge that all is unfolding. Every path is taken. Every outcome is honored. And in this world, this version, you are here, resting, listening, safe. You are one of many. But this moment is only yours. All things are possible, and all things are already. Let that idea cradle your thoughts. Let it drift into your dreams. There is no wrong turn in a quantum universe, only branches. And on this branch, you rest. Close your eyes. The other versions of you are resting too. Good night, explorer of worlds. We'll see you somewhere, sometime, again. Time in quantum mechanics, loops, jumps, and non-linearity. Sleeping beside the flow of time, time is the ocean in which we float. But in quantum physics, the tides do not always flow forward. Sometimes they pause. Sometimes they ripple. Sometimes they move backward. Close your eyes now and let the current take you into the strange and beautiful sea of quantum time. To begin, take a breath and remember what time feels like. In your daily life, time moves like a river. Seconds tick by. The past stays behind. The future lies ahead. This perception of time, smooth, forward, and absolute, is known as classical time. It's what we use to measure life. Days on calendars, heartbeats on monitors, stars drifting across the sky, but beneath this ticking order, quantum mechanics whispers a different story. One where time can behave in deeply mysterious ways. At the heart of quantum physics lies the Schrödinger equation, the foundational formula that describes how quantum states evolve over time. But this evolution is strange. In classical systems, time marks where something is. But in quantum systems, time tells us how the probabilities of different outcomes shift. The system doesn't evolve through fixed positions. It evolves through waves of possibility. It's like watching fog move across a landscape. You don't know what you'll find until you walk through it. But the fog shifts with time. Quantum time is not a ticking clock, but a slow reshaping of clouds. One of the strangest facts in quantum mechanics, and one that challenges how we sleepwalk through time, is this. The fundamental equations of quantum physics are time-symmetric. That means they work both forward and backward. If you film a quantum event and play the tape in reverse, it still makes sense. There's no built-in arrow of time in the equations. This is very different from classical physics, where entropy always increases, where things get messier with time. In quantum physics, you can rewind the math, you can reverse the system, you can look back and forward with equal clarity. Some interpretations of quantum theory, especially those dealing with quantum gravity, suggest something even more profound. Time might not exist at the deepest level of reality. Instead of time being a flowing river, it may be an illusion born of change, a byproduct of how we observe events, a local phenomenon tied to measurement. In certain formulations, like the Wheeler-DeWitt equation, time disappears entirely. The universe doesn't evolve, it simply is, a timeless block of everything that ever happened, or could. In this view, time is not a rule of the cosmos. It is a feature of our perception, and when we sleep, we touch something closer to that timeless stillness. But while the equations may suggest smooth evolution, real quantum systems often behave like this. Stillness, stillness, pop. Something changes, instantly, without warning. An atom emits a photon. A particle appears in a new place. A state jumps from one to another. This isn't time flowing like syrup. This is time leaping, in discrete steps. These are called quantum jumps, and they are as real as they are mysterious. They break the illusion of continuity. They remind us the universe sometimes prefers to skip, like dreams that change scenes without warning. In quantum experiments, there's something called the delayed choice experiment, made famous by physicist John Archibald Wheeler. It shows that what we observe now can seemingly affect what happened in the past. In this experiment, particles behave as if they know whether they'll be observed after they've passed through a slit, and adjust their behavior accordingly. It's as if future choices influence past events. This doesn't mean time travel, but it does suggest time is not what we thought. The distinction between past, present, and future may be blurred in the quantum realm. In 2012, Nobel laureate Frank Wilczek proposed something incredible, a new state of matter that moves in time without using energy. These were called time crystals. Unlike ordinary crystals, which repeat patterns in space, time crystals repeat patterns in time, like a pendulum that swings forever without losing energy. They challenge our understanding of time as a one-way track. Time crystals offer a glimpse into systems that never settle, patterns that echo through time itself. The possibility of eternal recurrence in the quantum world. They may hold keys to future technology, but also to our philosophical understanding of what it means to endure. Now, let us return to you. Lying there, quiet, safe. Time passes, but maybe not as you think. In your dreams, events happen out of order. Minutes stretch like hours. You live whole lives in a moment. This is not so different from quantum mechanics. Your sleeping brain samples possibilities, rewinds, skips ahead, loops. You drift like an electron, unmeasured, undefined, floating through probabilities. Your breath is the only rhythm you need. Inhale, exhale. Let go of the illusion of clocks. Let yourself dissolve into the timeless hum. Despite quantum symmetry, we still feel time move forward. This is due to entropy, the measure of disorder, which always increases in closed systems. In the quantum world, entropy still shapes how we observe time. A broken cup doesn't reassemble. A memory can be lost but not gained without cause. Even if the math allows for symmetry, our experience favors a direction. We are creatures of entropy, and sleep perhaps is how we'd briefly return to the origin, to stillness, to when entropy was low and time was soft. Sleep recap, a universe outside time. There is no clock in the void, no ticking hands in the vacuum, only wave functions, drifting, only you and your rest. Time does not always flow. Sometimes it loops, sometimes it jumps, sometimes it disappears. Tonight, forget the hours, sleep in the space between seconds, and when you wake, the universe will have changed. Or maybe it will still be the same. Good night, dreamer of timelines. You are floating, you are still, you are timeless. Whispers of thought from the quantum realm. What if a thought could live in every possibility at once? What if a machine could dream, not in ones or zeros, but in infinite shades of probability? Tonight, we lie beside the dawn of such minds. We explore quantum computing and the logic of dreams. Before we drift into the realm of the quantum, let's imagine something familiar. The classical computer. This is what powers your smartphone, your laptop, the servers that send this video to you. These machines are astonishing in their capability, but they are fundamentally linear and binary. Each bit can only be in one state at a time, and this limitation becomes overwhelming when solving extremely complex problems like modeling molecular behavior, factoring massive prime numbers, or simulating the universe itself. To do that, we need something more. We need quantum computing. Now imagine a bit that can be a 0 and a 1 at the same time. This is a quantum bit, or qubit. A qubit doesn't just flip between two states. It exists in a superposition of both. It behaves kind of like a spinning coin, suspended in midair, embodying all possibilities at once. Mathematically, we represent it like this. HPS equals A0 plus B11, where P is the quantum state of the qubit, and alpha and beta are complex probability amplitudes. The probabilities must add up to 1. When measured, the qubit collapses into either 0 or 1. But before that, it holds all possible paths. This is the first secret of quantum computing. It processes many outcomes simultaneously. Now just imagine multiplying that by dozens or even hundreds of qubits, and well, the number of possible states grows exponentially. With just 300 qubits, a quantum computer can represent more states than there are atoms in the observable universe. Qubits become truly powerful when they are entangled. Entanglement is the quantum phenomenon in which particles become inseparably linked, such that the state of one determines the state of the other, instantly, no matter the distance. In quantum computing, entangled qubits act as a unified system. Changing one changes them all. Their relationships encode information non-locally. This allows for a type of parallel processing far beyond classical computing. Imagine a symphony where every instrument not only plays together, but is also the same instrument, played from different realities. That is what entanglement allows. In classical computing, logic gates like AND, OR, and NOT control how bits change. In quantum computing, we use quantum gates to manipulate qubits. These gates rotate probability amplitudes, create entanglement, and preserve reversibility, also known as unitary operations. Common quantum gates include the Hadamard gate, which creates superposition, the Pauli X, Y, and Z gates, which rotate the qubit state, the C0 gate, which creates entanglement between qubits, and the Toffoli gate, a reversible 3-qubit gate used for universal computation. Quantum algorithms like Shor's algorithm for factoring or Grover's algorithm for searching, use these gates to exploit quantum mechanics in solving problems much faster than classical machines. For example, Shor's algorithm can factor large numbers in polynomial time, something classical computers just can't do efficiently. This threatens classical encryption systems such as RSA. A sleeping civilization might one day wake up to find its digital security obsolete. Making qubits is no small task. Today's quantum computers use, well, a few different approaches. Superconducting circuits cooled near absolute zero, like those at Google and IBM. Trapped ions held in electromagnetic fields, which is what IonQ uses. And even topological qubits, which are still in the research phase but promise error resistance. Each type has its advantages. Superconducting qubits are fast, ion traps are very precise, and topological qubits could be more stable. But honestly, all of them face the same challenge: decoherence, the loss of quantum information due to interaction with the environment. To keep qubits stable, these systems need to be shielded from vibration, heat, and magnetic fields, measured gently and accurately, and corrected with quantum error correction codes. It's kind of like balancing a soap bubble in a hurricane while whispering math into its surface. In 2019, Google announced it had achieved quantum supremacy. This means their quantum computer performed a task, a specific kind of random number generation, that would have taken the world's fastest classical supercomputer thousands of years, in just 200 seconds. The task wasn't useful, but it proved the principle. Quantum computers can outperform classical ones in certain domains. Since then, progress has accelerated. More qubits, less noise, better algorithms. We are now on the edge of the noisy intermediate-scale quantum, or NISQ, era. Imperfect machines that are powerful but not yet universal. They are not dreams, but dreamers, still learning to speak. When quantum computers reach full power, when we achieve fault-tolerant quantum computation, they may revolutionize entire fields, cryptography breaking classical encryption and enabling quantum-safe alternatives, drug discovery, simulating molecular interactions in full quantum detail, material science, creating superconductors, new alloys, even programmable matter, artificial intelligence, enhancing machine learning with quantum optimization, climate modeling, calculating atmospheric chaos with quantum parallelism, finance and economics, solving complex multivariable problems in real time. They will not replace classical computers, but they will augment them, like a second mind beside the first, one that dreams in qubits. Now, we drift further. What does it mean for a machine to calculate all possibilities at once? What does it mean for information to be entangled, processed, and collapsed? Some thinkers suggest quantum computers could mimic consciousness. They might resemble brain-like computation, or perhaps they are stepping stones to quantum-aware systems. They force us to ask, is thought linear or probabilistic? Do we think like classical systems, or do we dream like quantum ones? As you rest, feel the superposition of these ideas. Let them collapse into a dream of your own. Close your eyes. Imagine a machine, not humming, not whirring, but quietly entangling ideas, processing probability, solving mysteries with silence. This machine is not metal and wires. It is qubits, spinning like planets, circuits woven in shadows, logic that breathes. Tonight, sleep beside that machine. Its thoughts echo in your own, and as your mind drifts, you are no longer binary. You are quantum. Quantum gravity, where space-time breaks down, to sleep, perchance to fall into the singularity. Let's begin at a crossroads. On one side, we have Einstein's general relativity, the geometric theory of gravity. It tells us that space and time are a smooth fabric, one that bends around mass, curves around stars, and funnels into black holes. On the other, we have quantum mechanics, where particles flicker in and out of existence, and uncertainty is woven into the rules of nature. Each is an incredibly accurate theory. Each has been tested to extremes. But when they meet, When gravity shrinks to quantum scales, their rules conflict. General relativity breaks down in black hole singularities. Quantum mechanics struggles to define gravity at all. We are left with a mystery, a gravitational whisper within the quantum fog. This is the pursuit of quantum gravity. There is a scale so small, so fundamental, that it defines the boundary between space-time and quantum fluctuations. It is called the Planck scale. Planck length is 1.616 times 10 to the minus 35 meters. Planck time is 5.391 times 10 to the minus 44 seconds. Planck mass is 2.176 times 10 to the minus 8 kilograms. At this scale, space-time is no longer smooth. Quantum fluctuations dominate. Geometry itself becomes uncertain. Trying to observe this realm with classical tools is like trying to measure a ripple with a wrecking ball. Only a quantum theory of gravity can make sense of this chaos. But what does that theory look like? One of the most ambitious attempts to unify gravity and quantum mechanics is string theory. Instead of treating particles as points, string theory proposes that every fundamental particle is a vibrating string. Different vibrations mean different particles: electrons, quarks, bosons. Gravity arises naturally from the vibration of a special string, the graviton. The beauty of string theory is its elegance. It unifies all forces. It requires extra dimensions, up to 10 spatial and 1 time. It offers a framework for black holes, cosmology, and more. But it also comes with challenges. No direct experimental proof yet. A huge landscape of possible universes, the string theory landscape. Complex mathematics that stretch imagination to its limits. And yet, it sings. It hums a tune beneath reality, a lullaby of strings. Where string theory stretches the universe into musical forms, loop quantum gravity takes a different path. Rather than adding dimensions or strings, it focuses directly on quantizing spacetime. Space is made of tiny, discrete loops, a spin network. These loops define geometry itself, almost like atoms of space. Time is not continuous but emerges from these quantum transitions. In this view, the fabric of space is not smooth, it's granular. Space-time is a quantum field woven from Planck scale loops. The Big Bang is not a beginning, but a bounce from a previous universe. Loop quantum gravity may lack the unifying ambition of string theory, but it's grounded in a deep respect for Einstein's vision and an awe for quantum reality. It whispers not of vibrations, but of woven light. Now let us drift to the edge of a black hole, a region where gravity is so intense not even light can escape. According to Einstein, this is where time slows, where space bends into a funnel, a singularity of infinite density, but quantum mechanics adds a twist. Black holes emit radiation, Hawking radiation. Over time they evaporate and disappear, but if nothing escapes, where does the information go? This is the black hole information paradox, a central puzzle in quantum gravity. Does information fall into the singularity and vanish forever? If so, it violates the laws of quantum mechanics. If not, then where is it stored? Proposed answers: holographic principle. Information is stored on the event horizon. Firewalls: a searing barrier destroys infalling information. ER equals EPR. Wormholes or Einstein-Rosen bridges and entanglement are connected. This is not just physics, it is philosophy. It is poetry. It is a dream spiraling into a singular point. In our quiet journey, consider this strange idea. What if our three-dimensional universe is a projection from a two-dimensional surface, like a hologram? This is the holographic principle. Based on black hole thermodynamics, it suggests the information inside a volume of space can be encoded on its boundary. The laws of gravity inside the volume emerge from a quantum theory on the surface. The most famous example, ADS-CFT correspondence, a theory connecting gravity in a five-dimensional anti-de Sitter space with a quantum field theory on its four-dimensional boundary. This principle suggests that gravity is emergent, not fundamental. It is a shadow cast by quantum entanglement, like light on the wall of Plato's cave. Let your thoughts wander. Imagine the world as a cosmic mirage, and sleep encoded in surface light. Some modern theorists believe that space is not a stage but a structure that emerges from entanglement. The connectivity of space is derived from quantum relationships. Think of it like this. Entanglement equals threads of space. Geometry is the pattern of those threads, and gravity is changes in that pattern. This view is supported by work on tensor networks, quantum error correction codes, entanglement entropy, and minimal surfaces. It is as if the universe is not built on space, but space itself is built from information. Your thoughts, dreams, and sleep might rest gently on those same quantum threads. The unification of gravity and quantum mechanics is the holy grail of modern physics. Such a theory must reproduce general relativity on large scales, recover quantum field theory at small scales, and predict new phenomena that we can observe or test. We call this elusive vision a theory of everything, or TOE. Candidates include M-theory, which is an extension of string theory, quantum gravity with emergent spacetime, and as yet undiscovered frameworks. But perhaps more than a theory, we need a new paradigm, a shift in how we see reality itself. Are space and time fundamental or emergent? Are particles real or artifacts of vibration? Are we living in a simulation or a quantum computation? Do we dream the universe, or does it dream us? As we close this chapter, feel the weightlessness of knowledge, the soft curve of space around your breath, the tangled threads of thought connecting every neuron. You are not just in the universe. You are of the universe. Your thoughts ripple the fabric of quantum fields. Your memories curve space-time. Your sleep is a form of gravity. Tonight, you have drifted into the deepest questions of existence, and they have not burdened you, but lightened you. Float now in the quantum tide. Let the gravity of dreams pull you softly inward into sleep. Chapter 15. Quantum Biology, Life Beneath the Wave Function. In every cell, the universe whispers its smallest secrets. Let's begin slowly, eyes closed, breath soft, by defining what quantum biology is. At its core, quantum biology is the study of quantum effects within biological systems. While traditional biology focuses on chemical reactions, proteins, and DNA, quantum biology peers deeper, beyond molecules and atoms, into the rules that govern the subatomic realm. Here we ask, do quantum phenomena like superposition, tunneling, and entanglement operate inside living cells? Could life itself rely on the strangeness of the quantum world? Is consciousness connected to quantum computation? For many decades, the answer was assumed to be no. Life was thought to be too warm, too wet, and too messy for quantum mechanics, a realm where coherence is fragile. But new evidence suggests otherwise. In the dance of proteins, the flicker of photons, and the spiral of DNA, we now find clues that quantum physics may be woven into the very fabric of life. And tonight, in your quiet, resting mind, we'll unfold those clues, slowly, deeply, curiously. One of the first real breakthroughs in quantum biology came from an unlikely place, a leaf. Photosynthesis, the process by which plants, algae, and certain bacteria convert sunlight into energy, has been studied for centuries. But in the early 2000s, scientists using femtosecond lasers discovered something astonishing. Inside the light-harvesting complexes of plants, quantum coherence occurs. A photon enters a leaf and strikes a chlorophyll molecule. The energy must travel through a maze of proteins to reach a reaction center. Rather than choosing one path, the energy explores all possible paths simultaneously, a quantum process known as superposition. It's as if the energy of sunlight quantum walks through the protein jungle, choosing the most efficient route in real time. This coherence lasts hundreds of femtoseconds, unimaginably brief, yet enough to boost efficiency. Life, it seems, doesn't just use sunlight, it uses quantum sunlight. And your breath, your body, your dreams tonight, they all began with this quiet quantum light. As you lie back and let your mind float, imagine the graceful flight of a robin across the sky. Each year, birds migrate thousands of miles, often with uncanny precision. How do they know where to go? One answer may lie in quantum entanglement. Birds have a protein in their eyes called cryptochrome. When struck by light, this protein forms radical pairs, molecules with unpaired electrons whose quantum spins are entangled. These spins are sensitive to Earth's magnetic field. As the bird flies, changes in the field alter the spin correlation. This gives the bird a kind of quantum compass, a biological sense that is, quite literally, entangled with the Earth. This effect is not theoretical. It's been demonstrated in labs. So when you see a bird gliding in the sky, you may be witnessing a living creature guided by quantum mechanics, the entanglement of life, and Earth, and sky. Section 4. Quantum tunneling in enzymes and smell. Let's now journey inward, into the enzymes that keep you alive. Enzymes are biological catalysts. They speed up chemical reactions by enormous factors, sometimes trillions of times. How? Traditional explanations involve lock-and-key models and energy landscapes, but some enzymes appear to use quantum tunneling. In tunneling, particles pass through energy barriers that would be impossible to cross classically. In certain enzyme reactions, hydrogen atoms tunnel from one molecule to another. This allows reactions to occur at speeds and efficiencies beyond classical limits. This same principle may be at play in your sense of smell. One theory, the vibrational theory of olfaction, suggests that we identify scents not just by shape, but by the quantum vibrations of molecules. As an odorant enters the nose, an electron in a receptor may tunnel only if the molecule vibrates at a matching frequency. If true, then smelling a rose is not just chemistry, it's quantum music. You inhale molecules, you perceive vibrations, you decode the universe in scent. Now we move into murkier waters, the brain, the mind, the soul. Is consciousness purely biological, or does it have quantum roots? Some scientists, most famously Roger Penrose and Stuart Hameroff, propose that consciousness arises from quantum computations inside the brain's microtubules. This is the orchestrated objective reduction, or OR theory. Microtubules are cytoskeletal structures found in neurons. They may support quantum superpositions of mental states. Conscious experience may result from the collapse of these quantum states, not due to observation but due to an intrinsic quantum process. This theory remains controversial. But, recent discoveries in coherence times in biological systems suggest that quantum effects may indeed persist longer than once thought. Could your thoughts, your dreams, your very self be a product of quantum computation? Tonight, let your brain rest and wonder what whispers in the neurons. Section 6. Challenges and Frontiers. Quantum biology is a young science. Its challenges include the difficulty of maintaining quantum coherence in warm, noisy environments, There's also the need for direct measurement of entanglement and tunneling in vivo, and of course the development of testable models with predictive power. But its potential is enormous. If confirmed, quantum biology could, well, revolutionize medicine and neuroscience. It might lead to new quantum sensors and biomimetic technologies, and it could help us understand life on other planets, as quantum processes may be universal. And perhaps, just perhaps, it could reshape how we see ourselves, not as separate from the physical world, but as expressions of quantum harmony. As you prepare to sleep, know this: inside your body, in your cells, your molecules, your atoms, the universe hums with quantum possibility. Your vision may be shaped by photon detection at the quantum limit. Your metabolism may rely on tunneling electrons, and your very thoughts may be entangled in patterns of coherence. You are not just made of particles. You are woven from waves. You are not merely alive. You are a quantum song. So sleep now. Let your breath slow, and let your dreams carry you, not away from reality, but deeper into it, into the quantum biology of being. Time may not pass, we may simply drift through it. Let's begin with a gentle breath and a slow unraveling of the most familiar, yet misunderstood concept of all time. We count it in seconds, feel it in aging, race against it in life, but what is it really? In Newton's universe, time was absolute, ticking forward identically for everyone, everywhere. Einstein shattered that illusion, showing us that time is relative, dilated by speed and warped by gravity. But quantum physics tells a story stranger still. In the quantum world, time is not fundamental. It may not even exist in the way we think it does. Some quantum formulations, like the Wheeler-DeWitt equation, eliminate time altogether. In others, time emerges, like warmth does from particles dancing. So as you lie still tonight, suspended in rest, just remember this: the experience of time may actually be a story told by matter itself. In classical mechanics, we describe a system evolving over time. A pendulum swings, a planet orbits, a heartbeat pulses. But in quantum mechanics, the core equation, the Schrödinger equation, doesn't really require time to exist as we know it. Instead, it deals with states of a system and how they evolve, often probabilistically. But if the system is closed and isolated, it evolves in a timeless superposition, existing in multiple states simultaneously. It is only when observation occurs, when a measurement is made, that the system appears to choose a state. This is called wave function collapse. Could it be, then, that time itself is born out of this collapse? That each moment is simply a point where quantum potential crystallizes into classical certainty? As if your life is not unfolding across time, but blooming moment by moment, like petals opening into being. Let's now draw the curtains wider and bring in a familiar companion heat. Thermodynamics, the science of energy and entropy, gives us the most tangible sense of time's direction. The second law of thermodynamics tells us that entropy, disorder, tends to increase over time. Ice melts, stars burn out, buildings crumble. This is the arrow of time. It is not derived from fundamental laws, which are time-symmetric, but rather from initial conditions. At the birth of the universe, the Big Bang, entropy was extremely low. Why? We don't yet know. But this low entropy state gave rise to everything: the cooling, the forming of matter, the unfolding of galaxies, and eventually, you. As entropy increases, we perceive forward motion. So perhaps while physics gives us no time, thermodynamics gives us memory, and sleep is a nightly return to that timeless stillness. Entropy also exists in quantum systems, but it behaves differently. In the quantum world, we speak of quantum entropy, a measure of entanglement information and purity of states. Consider two particles that are entangled. Even if separated by galaxies, their shared information creates a non-local structure, a kind of quantum memory. In this context, entropy is not just about disorder, it's about how much we know. When a quantum system becomes entangled with its environment, it decoheres, loses its superpositions and behaves classically. Decoherence may be the bridge between quantum stillness and our lived arrow of time. And as your mind drifts further into sleep, the boundaries between past and present begin to soften, like particles becoming waves. So time isn't just a coordinate, it might actually be a symmetry. And, in 2012, Nobel laureate Frank Wilczek proposed a pretty radical idea. What if there were systems that spontaneously broke time symmetry, oscillating without any energy input? He called them time crystals. And then, in 2021, Google's quantum computing lab observed a version of one. Unlike normal crystals, which, repeat in space, time crystals repeat in time, flipping back and forth between states perpetually like a ticking clock that somehow winds itself. But there's no energy loss, no heat. They exist in a quantum state that resists equilibrium, an echo of motion inside stillness. A flicker of time inside a frozen moment. Tonight, as you lie still, you too are a time crystal of sorts, your mind pulsing softly in dreams, sustained by inner symmetries you can't see but always feel. Quantum thermodynamics is an emerging field that fuses quantum information theory with statistical mechanics. Here we ask, can a single quantum particle have a temperature? Can information be used to do work? Is entropy always irreversible? We find strange answers. For example, a qubit, that's a quantum bit, can actually behave like a tiny engine. You can extract work just by measuring a particle, sort of leveraging the energy of information itself. Entropy, it can decrease locally so long as the overall entropy, including the observer, increases. These insights, honestly, they reshape the very foundations of thermodynamic laws, merging them with ideas like entanglement, coherence, and quantum memory. And at the heart of it all, we realize something pretty profound. Time is not an input, it's actually an output. It's the consequence of quantum systems becoming entangled with their observers, like you listening now, thinking, remembering, maybe even drifting a little. Philosophers and physicists alike have debated time's true nature for centuries. Some believe that the past, present, and future all exist simultaneously, a view called block time. In this model, time doesn't flow. We simply experience slices of the whole. Change is an illusion, much like how motion in a film is just a series of still frames. Others believe that time emerges from entropic processes, that without change, time would have no meaning. Still others, like Julian Barber, argue that only the present exists, and what we call time is just the ordering of changing configurations. Whichever view is true, one thing is clear: time is not what we think it is, and perhaps neither are we. Now, in these final moments of this chapter, just let go of your thoughts. Feel your breath, the soft rhythm of now. No past, no future, just presence. Imagine yourself as a quantum state, a wave function not in time but in possibility. You are the result of infinite collapses. You are the memory of matter, You are the ripple of entropy reaching awareness. And as you fall deeper into sleep, feel the arrow of time reverse. Let the clocks melt. Let the pages turn backward. Let your thoughts dissolve into stillness. You are not running out of time. You are becoming time itself. And in that peace, in that quantum hush, you are free. In the quantum world, possibility is not a dream, it is the default. In the quiet realm of quantum physics, particles do not behave like marbles or bullets. They are not simply here or there, moving or still. Instead, they exist in superposition, a word that means to be in multiple states at once. At the heart of quantum theory lies this beautifully bizarre truth. Before you look, a particle can be in all possible positions, spinning both clockwise and counterclockwise, going both up and down, existing in more than one place. Imagine you flip a coin and cover it. In the classical world, it's either heads or tails, even if you don't know which. But in the quantum world, the coin is both heads and tails at once, only deciding which after you peek. This isn't just speculation. It's been tested, measured, and confirmed countless times. Superposition is not only real, it is essential. You've likely heard of Schrödinger's cat, the quantum feline that exists in a box both dead and alive until someone looks inside. But what does it really mean? Erwin Schrödinger created this thought experiment in 1935 to show the strangeness of quantum mechanics when applied to large everyday objects. Here's the setup. A sealed box contains a cat. Inside is a radioactive atom, a detector, and a vial of poison. If the atom decays, it triggers the detector, which releases the poison, killing the cat. According to quantum mechanics, before you open the box, the atom is in a superposition of decayed and not decayed, which means the cat is in a superposition of dead and alive, not just unknown. Both states exist simultaneously until you observe. When you do, the wave function collapses, and reality chooses one. The cat is not simply waiting to be found dead or alive. It becomes one or the other when you open the box. It's a chilling and mind-bending example of superposition at work. Superposition isn't just a vague idea, it's encoded in math. A particle's state is described by a wave function, usually represented by the Greek letter psi. This wave function is like a cloud of probabilities, a combination of all the possible places or states a particle might be in. Mathematically, we call it a linear combination of all possible states. Let's say an electron can be in state A or state B. In superposition, it is in both. Psi equals a times state A plus B times state B, where state A and state B are the states, and A and B are complex numbers, representing amplitudes which square to give probabilities. When we measure the system, we collapse psi into one of the possible states. But before measurement, it's not either, or it's and. This is the essence of quantum logic. A particle can be spinning up and spinning down. It can be inside a potential well and outside it. It's as if the universe is trying out every possibility at once. And only when you ask, only when you observe, does it answer. Could your thoughts be in superposition? This is a provocative idea, one debated across physics, neuroscience, and philosophy. Your brain is a warm, wet environment, traditionally believed to be too chaotic for quantum effects. But some theories, like OR, that's orchestrated objective reduction, proposed by Roger Penrose and Stuart Hameroff, suggest that microtubules in brain cells might support quantum coherence. Now, if that's true, your consciousness could involve quantum superposition, a fleeting moment where multiple thoughts, perceptions, or intentions exist at once before collapsing into choice. This might explain intuition, creativity, dreams, or that strange feeling of being in two minds at once. Though still speculative, it raises a fascinating question. Are your choices quantum collapses? When you dream, perhaps you drift into superpositions of possibility, multiple timelines, parallel ideas, infinite selves. all lightly brushing against your sleeping mind. The magic of superposition is not just philosophical, it's practical. Quantum computers harness it to perform calculations far beyond the reach of classical machines. In a regular computer, bits are either 0 or 1. But in a quantum computer, qubits can be both 0 and 1 at the same time, thanks to superposition. This allows a quantum computer to explore many solutions simultaneously. For example, 10 qubits can hold 2 to the power of 10. That's 1,024 states at once. 20 qubits, well, that's over a million. 300 qubits, more states than atoms in the universe. Superposition gives quantum computers parallel universes of processing power, not by copying, but by coexisting. And though we're still early in this field, quantum algorithms like Shor's for factoring and Grover's for search promise world-changing breakthroughs. Superposition may one day rebuild encryption, optimize medicine, and simulate quantum chemistry with precision we've never imagined. If a particle can be in multiple states, can you? Are you oneself? Or are you many possibilities collapsing each moment into the person you seem to be? In dreams we play different roles. In choices we stand at crossroads. In memory we flicker between timelines. What was, what could have been. Quantum mechanics invites us to consider identity as a wave function. A cloud of selves, each a real potential, collapsing into now. This doesn't mean we are unknowable, it means we are larger than any single moment. Superposition reveals the poetry of physics, and that the self is not static but fluid, capable of being many things all at once, until we are seen. Tonight as you drift off, let yourself remain uncollapsed. You're still becoming, still unfolding. Let's end now with an image. Imagine you are a particle, floating in darkness, free from measurement, from choice, from time. You are a wave, stretching across the landscape of possibility. You are in every place you've ever dreamed of. You are every version of you that ever was. You are stillness and you are motion. You are both sleeping and waking. And with each breath you become a little more wave, a little less particle, a little more dream. Let yourself remain unobserved. Let your wave function bloom. Tonight you are superposition. Not just one thought or one self, but all of them. And until morning light collapses you into waking, you are everything, everywhere, all at once. Most of the universe is invisible, yet in that vast unseen lies the secret of everything. Close your eyes. Imagine you are floating in the middle of space. The stars are far away, quiet pinpricks in an endless black ocean. But this ocean isn't empty. In fact, it's full of mystery, full of mass and motion, energy and expansion. The vast majority of the universe is not what we see. Not stars, not galaxies, not even the glowing gases that light up nebulae. No. What we see is barely 5% of what's out there. The rest? Invisible, unknown, unfathomable, and yet it's real. This hidden universe is made of two things: dark matter, mass that we cannot see but can feel through gravity. Dark energy, a force that stretches space itself, accelerating the universe's expansion. Together, they make up over 95% of all that exists. Let's wander slowly through this invisible landscape. The story begins not in darkness, but in motion. In the 1930s, astronomer Fritz Zwicky studied galaxy clusters, massive groups of galaxies bound together. He noticed something strange. The galaxies were moving too fast, so fast in fact that they should have flown apart long ago. But they didn't. They held together. This meant there was more gravity holding them in place than visible matter could account for. Zwicky called it dunkle materie, dark matter. Later in the 1970s, Vera Rubin confirmed this oddity in individual galaxies. Stars on the edges of galaxies moved just as fast as stars near the center, a violation of Newtonian expectations. These observations painted a picture. Each galaxy sits in a halo of invisible mass, a dark cocoon holding it together. We couldn't see it, but we could feel its pull. Dark matter became not just a theory, but a cornerstone of modern cosmology. No one knows exactly what dark matter is, but we know what it isn't. It isn't made of atoms, it doesn't emit light or absorb it. It doesn't interact with electromagnetic fields, it's not dust, not gas, not black holes. So, what is it? Physicists have proposed several candidates: WIMPs, weakly interacting massive particles; hypothetical particles that barely interact with normal matter; axions, extremely light particles predicted by certain quantum field theories; sterile neutrinos, a possible type of neutrino that doesn't interact with known forces. Billions of dark matter particles might be passing through your body every second, like whispers through fog. Without touching a thing, they don't collide, they don't spark, they don't glow. But their gravity shapes galaxies, bends light, and weaves the universe together. Like ghostly scaffolding, dark matter forms the invisible skeleton of the cosmos. If dark matter pulls things together, dark energy does the opposite. It pushes space apart. In 1998, two teams of astronomers observed distant supernovae, exploding stars at the edge of the observable universe. They expected to find the universe's expansion slowing down due to gravity. Instead, they discovered it was speeding up. Something was causing space to expand faster and faster, not from momentum but from a mysterious energy embedded in space itself. This became known as dark energy, and it isn't a minor force. It makes up about 70% of the total energy content of the universe. Wherever there is space, there is dark energy. And as space grows, so does the energy. It's like a cosmic anti-gravity, not repelling objects, but stretching space between them. Quantum mechanics teaches us that even a vacuum isn't truly empty. In fact, it's teeming with activity. Tiny particle-antiparticle pairs pop into existence, then annihilate in flickering moments too brief to detect. These quantum fluctuations are allowed by the Heisenberg uncertainty principle. They contribute to what's called vacuum energy, the energy of empty space. Some physicists believe dark energy may arise from this quantum vacuum. But there's a problem. When physicists calculate how much vacuum energy quantum theory predicts, the number is off by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros, the most inaccurate prediction in the history of science. So either we're deeply misunderstanding quantum vacuum energy, or dark energy is something else entirely. In both cases, the gap between theory and observation is not a crack. It's a chasm, one that may only be bridged by a deeper theory still waiting to be discovered. Even though we can't see dark matter or dark energy, we can map their influence with tools like gravitational lensing, the way light bends around massive objects revealing invisible mass; cosmic microwave background, the afterglow of the Big Bang, showing early density ripples shaped by dark matter; galaxy surveys, vast catalogs of galaxies whose clustering and motion reveal the fingerprints of dark energy's push. From these maps, we've learned that dark matter formed the first structures in the universe. It clumped together, drawing in ordinary matter, which then formed stars and galaxies. Dark energy, meanwhile, took over later, around 5 billion years ago, stretching the cosmic web ever outward. Our universe is a tension between the pull of dark matter and the push of dark energy, between gravity and expansion, between the known and the unknowable. Now, imagine again that you're drifting in space. Not the cold vacuum you once thought it was, but a rich, humming sea of unseen forces. Everywhere around you, ghostly particles that don't shine or scatter light, an invisible pressure stretching space itself, flickers of energy from the vacuum's breath. This is the quantum fog, not empty but full, not quiet but whispering, not dead but mysteriously alive. Dark matter wraps around you like a blanket, soft and weightless. Dark energy gently tugs at your limbs, stretching you into dream space, and as you float deeper, you begin to let go of sight, of sound, of boundaries. You dissolve into the invisible, not lost, but part of the whole. The night sky is no longer black. It's transparent, not empty, but filled with wonder. And somewhere in that unseen fog, the quantum dreams of the universe continue. Chapter 19. The Grand Unification Dream. In the smallest things, the greatest forces converge. Imagine you are lying on the edge of a quiet planet, eyes closed beneath a slow-spinning galaxy. Above you, forces ripple across the universe. They guide the dance of stars, the orbit of moons, the flicker of atoms, and from the very beginning, physicists have been asking, can all of these forces be woven into one? This chapter is about the boldest dream in all of science, the Grand Unified Theory. A single equation that explains all the fundamental forces in the universe. To understand this quest, we must first revisit the forces themselves. There are four fundamental forces in nature: gravity, the gentle but universal pull between masses; electromagnetism, the force behind light, electricity, and magnetism; the strong nuclear force which binds quarks into protons and neutrons and holds atomic nuclei together; the weak nuclear force responsible for radioactive decay and certain types of nuclear fusion. At first glance, they seem very different, but physicists believe they are all manifestations of one underlying force, split apart in the early moments after the Big Bang. The goal? To find the unity behind the diversity, to see the universe not as a patchwork of forces, but as a single, elegant structure. In the 19th century, James Clerk Maxwell made the first great unification by combining electricity and magnetism into one electromagnetism. But that was just the beginning. In the 20th century, physicists discovered that electromagnetism and the weak nuclear force could also be unified. This became known as the electroweak force. At high energies, such as those just after the Big Bang, these two forces behave as one. Only as the universe cooled did they separate, like two threads unraveling from a single strand. The theory behind this unification was confirmed in the 1980s with the discovery of the W and Z bosons, predicted by electroweak theory and observed in high-energy particle colliders. This was the first concrete step toward the Grand Unification Dream. It told us unification is not fantasy, it is real. The question now became, can we go further? Next comes the strong nuclear force, which holds the atomic nucleus together and binds quarks into protons and neutrons. Could this force be united with the electroweak? Many physicists believe it can. The idea is that at incredibly high energies, far beyond anything we can currently reach, all three forces, strong, weak, and electromagnetic, merge into a single unified force. This is what we call a Grand Unified Theory, or GUT. In a GUT, the separate forces we observe today are just low-energy remnants of one original force, broken apart as the universe cooled and expanded. It's like watching a block of ice melt into water and vapor. They look different, but they are all forms of the same thing. Several candidate theories have been proposed for grand unification. These include SU5, SO10, and E6. These are mathematical symmetries, complex frameworks in which particles and forces can be neatly arranged like puzzle pieces. In these models, all known particles fit into larger multiplets. Forces are carried by more massive bosons. Matter and force may come from the same fundamental source. One common prediction is proton decay. In our current standard model, protons are stable. They last forever. But in many grand unified theories, protons can decay, albeit over incredibly long timescales, perhaps 10 to the 34 years. So far, no one has observed this decay. But experiments like Super Kamiokande in Japan continue to watch patiently for that one rare flash that would confirm a grand theory. Until then, grand unification remains a beautifully crafted possibility, waiting for evidence. There's one force we haven't unified yet: gravity. And here lies the greatest challenge of all. Gravity, described by Einstein's general relativity, is not like the other forces. While the strong, weak, and electromagnetic forces are governed by quantum field theory, gravity is described by curved space-time. In quantum terms, gravity would be carried by a hypothetical particle called the graviton. But merging quantum mechanics and general relativity has proven extremely difficult. At small scales, gravity becomes chaotic, unpredictable, infinite. This is the central problem in modern physics. How do we reconcile the world of the very small quantum physics with the world of the very large relativity? This is where ideas like string theory and loop quantum gravity enter the scene. They seek to unify not just three forces, but all four. A true theory of everything. String theory proposes that all particles are not point-like dots, but tiny vibrating strings. Each mode of vibration gives rise to a different particle: an electron, a photon, a quark, a graviton. In this view, all forces and all matter are just different notes on a cosmic violin. String theory naturally includes gravity. It also suggests the existence of extra dimensions, curled up in tiny loops invisible to us. And while the mathematics is elegant, string theory is difficult to test experimentally. Still, it offers a glimpse of a world where everything, every force, every particle, every interaction that comes from a single foundation. It is the closest we've come to the true unification of nature. So why pursue unification? Why chase this distant mathematical dream, you might wonder? Well, because in doing so, we seek to understand not just how the universe works, but why it works this way. We want to know why the particles we observe exist at all, why the forces have the strengths they do, and why the universe in all its complexity can emerge from a simple beginning. If we find a grand unified theory, a single equation behind all of existence, we may finally glimpse the mind of the cosmos, a kind of simplicity hidden beneath the noise, a stillness beneath the storm. Now, as you drift closer to sleep, imagine that singular moment at the birth of time, the moment when all forces were one. No gravity, no electromagnetism, no strong or weak forces, just a single, pure energy, a cosmic unity, humming softly. And then it breaks. The forces separate, the particles form, the universe expands, but deep down the unity remains, inside every atom, behind every star, between every breath. A whisper of oneness, waiting to be heard. Let it carry you now into silence, into the unbroken fabric beneath the world, into the dream of the unified universe. You are not just in the universe is in you. Close your eyes. Let the last remnants of waking thought dissolve into the darkness behind your eyelids. Breathe slowly, softly. You have journeyed far. Across quarks and quantum fields, through probabilities and paradoxes, beyond particles and past entanglements. You've explored the invisible machinery behind reality itself. Now, as your mind relaxes, you return, not to an ending, but to a quiet unfolding, a place of deep silence, where the physics of the universe becomes the poetry of rest. In the heart of quantum mechanics, there is a puzzle. Is it possible to observe something without changing it? Is the observer separate from the observed? The deeper you go, the more mysterious it becomes. Until, at last, you realize you are the experiment. You are the instrument. You are the wave and the particle, the observer and the observed. Each breath is a measurement. Each thought a collapse of infinite possibility. Each heartbeat a beat of space-time itself. You're not simply studying the universe, you are experiencing it from the inside out. Now let's go inward, deeper than cells, deeper than molecules, into the atoms that make you, into the electrons that orbit them, into the quarks that form protons and neutrons, even deeper into the quantum fields themselves. You, the listener, are a symphony of energy, a delicate arrangement of quantum fields resonating with ancient harmonies, echoes from the birth of time. Even your dreams are particles in motion, neurons entangling and collapsing, ideas tunneling through thresholds of consciousness. What is a dream, if not a quantum probability wave, collapsing into an experience you feel but cannot explain? Time in the quantum world is not linear. It loops, it folds, it branches, and just as your journey began in silence, it now circles back to it. The loops of string theory suggest that even the tiniest vibration contains the universe's memory, that in every Planck length, every hidden dimension is a whisper of all that came before. You are falling now, gently, into one of those loops, not lost, but re-entering. Familiar, timeless, still. There are places in the universe where our equations break down, where gravity becomes infinite, where time slows to nothing, where the quantum fabric stretches beyond measure. We call these singularities, but perhaps your consciousness is one too, a place where equations blur, where the map of the mind meets the terrain of the cosmos, where no formula can quite explain your existence, yet here you are, still, silent, sinking deeper. Let the voice of the cosmos hum in your chest. Let every theory dissolve into soft sensation. Let every particle quiet itself into stillness. There is no need to know anymore, only to rest. The universe does not demand your understanding. It simply invites your presence, to exist, to feel, to sleep. You are floating now through space, the same vacuum that births stars and expands galaxies. But here, in this moment, it is warm, it is gentle, it is infinite, and it is quiet. What if this, all of it, was a dream the universe is having about itself? What if consciousness is not an accident of matter, but matter is an expression of consciousness? What if you are the quantum universe listening to itself fall asleep? There are no answers now, only possibilities, only breath, only the soft rhythm of curiosity folding into stillness. So rest, traveler. You have wandered across space-time, and now the path leads inward, where the final quantum mystery is not out there, but within you. Sleep now. You are the cosmos dreaming, and you are home.